Bye. Bye, Chicky.
அதான் ஒரு தண்ணி விட போறோம்.
Can you hear me? Dear participants.
Yes, sir. We can hear you.
Hearing, sir.
So I am starting to share the presentation.
Sure.
Kalyan, sir. Kalyan, sir.
Yes, just a minute. Just a minute. Can you find the screen?
Yes, sir.
I am
But,
going to present. It is
okay.
okay?
Yes, sir. But before
Yes.
that, sir, I would like to give a brief introduction of you to all
Okay,
the.
okay.
Okay, sir.
Please
Okay.
start.
Now we will start a course with a 2-hour session on recent research work on microstrip antenna and frequency selective surface by Dr. Partha Pratim Sarkar, Professor, DTS Kalyani University. Dr. Pathak Pratim Sarkar obtained his PhD in engineering from Jadavpur University in the year 2002. He has obtained his ME from Jadavpur University in the year 1994. He earned his BE degree in Electronics and Telecommunication Engineering from Bengal Engineering College in the year 1991. He has 5 years industry experience from 1991 to 1996 in Webfield Limited as an executive system engineer. He has 26 years teaching experience from 1996 to 2022. He is presently working as the rank of professor at the Department of Engineering and Technological Studies, University of Kalyani, West Bengal. His area of research includes microstrip antenna, microstrip filter, frequency selective surface, and artificial neural network. He has successfully completed 5 research projects funded by AICTE and DRDO. Total 21 number of PhD degree awarded and 5 number of research scholars are working under his supervision. He has contributed to numerous research articles in various journals and conference of repute. He is a life fellow of IETE and IE. Over to you, sir.
Okay, thank you, madam. So I am starting my presentation. May I start?
Yes, sir.
Okay. Good morning, dear participants. I am starting to discuss about recent research work on microstrip antenna and frequency selective surface. Actually, in this discussion, there are 3 parts. Number 1, microstrip antenna. Number 2, what are the ill effects of antenna or electromagnetic radiation? And number 3, how may I take the remedial steps or protection from these evil effects of antenna with the help of frequency selective surface? So first we should know what is antenna. Before going into details of microstrip antenna, we should know what is an antenna. Basically, antenna is a device which helps to radiate power from a transmitter to free space or to receive power from free space towards a receiver. That means antenna is a transitional. Hello? Hello? Any problem?
No, sir. No, sir.
Okay. That means antenna is a transitional device between free space and a guiding device. What do you mean by guiding device? Guiding device may be coaxial line or a waveguide. Now, regarding bandwidth of an antenna, you can see here that reflection coefficient has been plotted against frequency, and where minus 10 dB line is indicated by two vertical lines. That means between these two vertical lines, that is at the range of around 2.2 to 2.7 gigahertz, reflection coefficient of this antenna is less than minus 10 dB. Less than minus 10 dB means reflection coefficient is less than 1 by 10. That means if power is fed to an antenna, 90% power will be radiated and less than 10% power will be reflected back. That region is called the operating region or bandwidth of the antenna. Reflection becomes more than 10%. That means radiation becomes less than 90, reflection becomes more than 10, reflection more than 10 and radiation less than 90. That will not be considered as operating band of an antenna. So first, whenever we shall design an antenna, that may be a general antenna, that may be a horn antenna, that may be a microstrip antenna, we should know what is the operating region of the antenna. After knowing the operating region, we shall have to indicate, we shall have to know, we shall have to realize what type of radiation pattern may I get from this antenna. What type of gain may I get from this antenna? Generally, radiation pattern of microstrip antenna becomes like the figure which is being shown in the presentation. An isotropic antenna, that is an ideal antenna. In that case, generally radiation takes throughout spherical type. Spherical type means 360 degree in azimuthal and 360 degree in horizontal position. But generally, radiation pattern of microstrip antenna or horn antenna and the directive antennas, their radiation pattern becomes like this, that is beam width becomes narrow. And regarding here, see that this is the radiation pattern of a general antenna. Say total 10 watt power is being radiated from here. If we feed 10 watt power and make the antenna isotropic, then its radiation pattern becomes like this spherical. If 10 watt power is fed to an ideal isotropic antenna, radiation pattern becomes like this spherical. But in an actual antenna, radiation pattern becomes like this, that is yellow colored. And the highest length, say this is x, and radius of the spherical pattern, say that is y. So x by y is called directivity of the antenna. Now, what is the structure of a microstrip antenna? A microstrip antenna is a planar antenna having a dielectric layer between two metal with a feeding point. That is, above the dielectric substrate there is a metal layer that may have any type of geometrical shape, and at the bottom of the dielectric substrate there is another metallic layer, and that layer is called ground plane. You can see here in more detail the yellow colored metal patch above the dielectric substrate, that is white colored. That is white color here indicates dielectric slab. Above the white color, that is above the dielectric slab, there is a yellow colored metallic patch. This is called radiating plane. And below the dielectric slab, there is another yellow colored ground plane. This is also metallic, and this is called ground plane. Generally, thickness of metal, that means thickness of radiating plane or ground plane, that becomes less than equal to lambda 0. Lambda 0 is the effective wavelength of the operating frequency. Now, what are the advantages of microstrip antenna? Generally, microstrip antennas are lightweight, have a small volume, and low profile planar configuration. They can be made conformal. That means you can fit them anywhere. Even you can fit them like a wristwatch. Ease of mass production. That means you can make a huge production using printed circuit board technology, and its cost is very low. They can be made compact for personal use in communication. They may be used in multi-frequency operations also. But why we should go into the research of microstrip antenna? If there is any problem, only then research starts. The problem of strip antenna is basically two. Its bandwidth is very narrow, its gain is very lower. So we shall have to go into detail of the research so that bandwidth may be broadened, gain may be enhanced. So what is our objective? Objective is to enhance the bandwidth, to increase the gain, to make it compact, and to design the antenna for multi-frequency operation. Then what will be our profit? This is written here. If antenna is made compact, then compactness of communication device of course takes place. If antenna becomes more compact, say your cell phone may be more compact. If bandwidth is enhanced, more channels per band may be accommodated. High gain. If you can increase the gain of microstrip antenna, it may be useful for radar systems. Now, before going into design detail of microstrip antenna, you should know what are the popular analysis techniques by which you can mathematically come to know about the properties. Properties means their gain, radiation pattern, reflection coefficient, bandwidth, etc. of a microstrip antenna. Is it possible to know these properties, not going into detail about fabrication? Yes, it is possible. And for this, there are three methods are used. Number one is transmission line model. Number two is cavity model. Number three is full wave analysis model. In comparison to first two methods, the third method, which is called full wave model method, its accuracy is very high, versatility is high, and it can model any arbitrary antenna. And this there are generally three types of modeling are being used in this method. Number one is called finite element method. Number two is called finite difference time domain method. And number three is called method of moment. Third one is the most versatile. Say, if you can compare these three methods, third method is most complicated. But advantage is that its accuracy is highest. And depending upon these three methods, there are several softwares which are being used commercially. Number one is FECO. This is based on MOM or FEM. Number two, ANSYS, HFSS and Designer. This is also based on MOM and FEM. Number three, CST Microwave Studio. It is based on finite difference time domain or FDTT method. And number four, I3D. This is based on method of moment. And you can design any customized software also, which is called self-developed by computer programming. Now this is regarding simulation method, that is theoretical analysis of the antenna. Now if you want to make fabrication and want to measure the antenna, what will be the measurement setup? It is very costly. If it is up to 40 gigahertz, measurement setup cost is around 1 crore. This slide, which you are finding, it is the setup for radiation pattern or gain measurement. Here there is a sensor and power meter, and in other side there is a microwave generator. And for return loss or reflection coefficient measurement, generally vector network analyzer or VNA is used. This equipment is most complicated and costly. If it is up to 40 gigahertz, only cost of this equipment is on around 1 crore. Now you can understand why the research activities regarding microstrip antenna is required. As it is of very low volume, you can accommodate in a very hand compact device like cell phone or missile or like that. But problem is that bandwidth is very narrow, and number two, its gain is low. In order to overcome that problems, research activities started around 40 years back. So our first work is to enhance the bandwidth. For bandwidth enhancement, generally 4 procedures are there. Number one is called regularly shaped broadband MSA microstrip antenna. Here generally slots or slits or apertures are loaded. Different geometrical slots are loaded on radiating patch or in the ground plane of the antenna. Number two, multi-resonator broadband MSA. Generally, here staggering effect is used to broaden the bandwidth. Number three, multi-layer broadband MSA. Generally, here 2 or 3 layers of dielectric slab and metal surfaces are used to enhance the bandwidth. And last, or number 4, is broadband planar monopole antenna. Generally, in this method, monopole antenna is being used. The first one, regularly shaped broadband MSA. Here, you can see that on the top of the figure, there is a triangular shape, and inside the triangular shape, there is a U shape. This triangular shape is totally metal, and that U shape is etching of metal. Etching of metal means at that position, metal patch has been removed. In the below position of the figure, there is another triangular patch and some definite geometrical light aperture has been loaded. That means from that portion, metal has been removed. And here one theoretical and practical results I am showing. Light at the top and right hand side, there is a rectangular radiating plane. In the rectangular radiating plane means metallic patch is rectangular. And in this metallic patch, rectangular metallic patch, the U-shaped portion, in this U-shaped portion, metal has been removed. Whenever metal has been removed, its bandwidth has been enhanced. Say, here bandwidth is from 0.8 gigahertz to around 1.3 gigahertz. And its percentage bandwidth is around 40%. What do you mean by percentage bandwidth? Percentage bandwidth means total band divided by resonant frequency. Here total band is 1.3 minus 0.8. That means it is around 0.5, and that is divided by 0.85, and this gives 40%. And if this slot is removed, that is, removal of metallic patch is not done, if it is not done, its bandwidth becomes only 2%. So by loading slot or removal of metal from some position, bandwidth is being enhanced from to 40%. Here another example is given here. Here is a square patch which is shown at the left side of the slide, and inside the square patch a U slot, U type slot, that is metal has been removed in this U position, and another position that is like this rectangular one above the U shape. From here also metal has been removed. As a result, bandwidth has been enhanced from around 1.2 to 2.2. That is around 1 gigahertz bandwidth has been achieved. 1 gigahertz is bandwidth, resonance is around 1.8. That is percentage bandwidth is around 50%. If this modification is not done, bandwidth becomes only 2%. And this is the second method. This is called staggering effect. Say a microstrip antenna is radiating past like L2, and on left side there is another patch L1, and on right side there is another plus patch L3. and that means here is multi-resonator. If only L2 exists here, it called single resonator. Here there are multi-resonator antenna L1, L2, L3. Now you can find from the slide that say directly feeding is given to the position with dimension L2, W2, which is called patch 2. And feeding is also done in patch 1, whose dimension is L1 into W1. Other than that, there are two more patches. 3 into W3 and another is L4 into W. That is 4 patches are here. And for one patch, you should have one resonance. So in the graph, you can see that there is a first resonance at around 2.7 gigahertz. That is at 2.7 gigahertz. This is around 2.8 gigahertz. Third resonance is at around 2.9 gigahertz, and fourth resonance is around 3.061 gigahertz. That is, these 4 resonant frequencies are being staggered to show a broad bandwidth with 12.7% percentage bandwidth. This is done by staggering effect. This is another example. 3 resonators are here, L1, L2, L3, and by staggering effect, here bandwidth enhancement has been up to 27%. If you remove L1 and L3, only L2 is present, say only L2 is present, then percentage bandwidth becomes just 2%. Whenever L1 and L3 are present by the sides of L2, then total bandwidth of the antenna, percentage bandwidth of the antenna becomes 27%. Next, multi-layer broadband. Multi-layer means like this. Say, the figure which is shown below of the slide, at the bottom there is ground plane. After that, there is a dielectric slab with dielectric constant epsilon r. Above it, there is metallic plane. General construction of a microstrip antenna. But here, above the metallic plane, there is another dielectric slab with dielectric constant R1. And above it, again there is another metallic plane. That is, it is multi-layered microstrip antenna, and it provides greater bandwidth. And number 4, which is very important and very effective nowadays, this is called monopole antenna. What do you mean by monopole antenna? In general, you find up to this that if you take an projection of radiating plane, ground plane will be just below the radiating plane. In this slide, in the topmost figure, first there is metallic patch and below it there is ground plane. You can see that the ground plane is just below the metallic patch. This is general microstrip antenna. Now in below left hand side, say this metallic patch is modified like this. That is, there is a horizontal line and then it becomes vertical at the left hand side. After that, below and in right hand side, say bottom ground plane is removed and ground plane is just vertical. So if you projection of metallic patch, that is, if you consider the below position of metallic patch, there will be no ground plane. Below the metallic patch, there is no ground plane. This is called monopole antenna. But what is the advantage and disadvantage of monopole antenna? Monopole antenna, its advantage is that this, among the other methods, monopole antenna has been reported to give the highest bandwidth. Percentage bandwidth maybe 150%, maybe 160% like this. But its disadvantage is its gain is very low, less than 3 dBi, 4 dBi like this. So it is a tremendous problem. You cannot use it practically. So our research should be such that we shall have to design monopole antenna, but we should try to increase its gain. This is one type of monopole antenna. The middle one is the radiating plane and outer one is the ground plane. You can see here that below the radiating plane there is no ground. So this is monopole concept. And in this monopole concept, you can see here that the bandwidth has been 2 gigahertz to 18 gigahertz. That means how much? It is around 16 gigahertz bandwidth. 16 gigahertz bandwidth and resonance frequency is around 6 hertz. So percentage bandwidth is 16 divided by 6 into 100%. That means more than 200%. Its normal bandwidth is around 16 gigahertz. Tremendous bandwidth. And it is designed in such a way that that disadvantage has been removed. That means its gain is greater than 3 dBi. That is gain from 3 to 9 dBi. Here another monopole antenna has been designed. The WPLP, this is the dimension of radiating patch, and LGWG is the dimension of ground plane. Below the radiating plane there is no ground plane, and here is we achieve tremendous bandwidth from around 3 gigahertz to 12 gigahertz. Here is another monopole type antenna. Though it is monopole antenna and its gain is more than 150, bandwidth is more than 150%, its gain is greater than 3 dBi and it is up to 6 dBi. This gain is sufficient for practical use. So we can enhance the bandwidth of microstrip antenna by 4 methods. And if bandwidth is enhanced, what is the advantage? More channels can be accommodated. And next here, you can see that by introducing some slots and slits, here 3 slots and slits have been introduced inside the antenna, and it operates in multi-frequency. That is, resonance is at 1, 2, 3, 4, 5. That is, at 5 frequencies the antenna can resonate. And it is very helpful in stealth technology. Stealth technology means, suppose your radar and your aeroplane is operating. From your radar, the first resonant frequency is being transmitted and it is received by your plane. Now enemy is trying to track your signal. If you can change first resonant to second to third to fourth to fifth, then it will be very difficult for the enemy to track your signal. So multi-frequency operation of an antenna will help you to operate the radar or to operate the antenna at different frequencies without using multiple antenna. And another important thing is compactness. Say, if you want to make an antenna at 10 gigahertz, say its area is 10 square millimeter. To design an antenna of 10 gigahertz, required area is say 5 or 6 like that square millimeter. Now, if you want to design an antenna at 2 gigahertz, its dimension will be much more. It may be 50 square millimeter. So whenever you want to reduce the frequency, dimension or area of the antenna will be 10 times, 7 times like that. So we have tried to reduce the frequency without increasing the area or dimension of the antenna, and that has also been possible. Here you can see that in the reference antenna it is operating at 3.1 gigahertz, and after modification, that is, a slot has been introduced in the ground plane. You can see at the left side of the slide, a slot has been introduced inside the ground plane, and as a result, this 3.1 gigahertz resonance has been shifted to 1.4 gigahertz, around 1.4. This is nothing but the size reduction of the antenna. As if you want to design an antenna at 1.4 gigahertz, its size would be at least 5 times greater than this antenna size. So you can achieve this lower frequency by the same dimension of the antenna. This is called size reduction. Now, these are all about microstrip antenna designs. Why I am discussing about the microstrip antenna design? Because almost more than 50% of radiation among our society is from cell phone tower or cell phones, and generally in cell phones or in handheld electronic devices, microstrip antennas are being used. Research is being done, and different modifications are in existence, and they are being used in our society. As a result, from this microstrip antenna, tremendous amount of electromagnetic radiation is being transmitted or radiated in our environment. Now, what is the harmful effect of electromagnetic radiation in the environment? I can think that you can understand what is the problem if you are exposed before the EM wave for a long time. I'm explaining. Number one, tremendous leap in the demand of cell phone technology. There is increasing use of microwave oven, and it results in uncontrolled and unmonitored installation of cell phone base station, especially in densely populated areas. Presently, disinfection and decomposition of biohazard waste using microwave is also done. This also increase in harmful radiation in urban areas. That means harmful radiation increases in both urban and rural areas. And what is its ill effects? For that, Professor Girish Kumar of Bombay IIT, Government of India requested Professor Girish Kumar of Bombay IIT in 2010 to submit a report regarding the ill effects of electromagnetic radiation to the society. And Professor Girish Kumar has made a vast studies on ill effects of electromagnetic radiation. And I am mentioning just by point by point, I am not explaining in detail. Microwave radiation may be harmful for a pregnant woman. Microwave radiation can damage the placental barrier due to presence of high water content in the amniotic fluid protecting the fetus. If a pregnant woman is exposed very much to electromagnetic radiation, it may be harmful. Number 2, large number of birds like pigeons, sparrows, swans die each year due to interference from the cell tower radiations. Number 3, it is found in some places production of wheat and corn has been badly infected, and this is for the electromagnetic radiation, not only for electromagnetic radiation, for excessive EM radiation. Microwave radiation may harm mental health of human being also, and this radiation may also cause hormonal imbalance. Now, to protect from these ill effects of EM radiation, what measures can we take? Frequency selective surfaces are electromagnetic filters which filter or reflect or transmit or absorb the electromagnetic waves based on the frequency of the waves. Properly designed FSS, I am going into detail about FSS, properly designed frequency selective surface and construction of building or protecting gear or waste treatment chambers using it shall be helpful in preventing the ill effects from the radiation of waves. I'm going into citing some examples. Say there are hospitals and healthcare centers where the use of mobile phones is in general prohibited. The walls of the ward of specific patient, suppose there is a patient, heart patient, and he has pacemaker. So walls of the ward of that patient may be constructed with a layer of frequency selective surface. Then EM wave will not enter that ward. This shall prevent the electromagnetic radiation of high strength from entering the area. Thus the ailing patients can be protected from the radiations. And in agriculture field, properly designed FSS can also be used in agriculture in rural areas which shall prevent the radiation from the cell towers. I'm trying to explain. Suppose it is seen, say, two wheat fields are 5 kilometers apart. One is exposed to EM wave, another is not exposed to EM wave. The field which is not exposed to EM wave, it is not affected, its production is okay. But wheat field which is exposed, heavily exposed to EM wave, it is found that its production is badly affected, production reduced. So we can use just a screen of frequency selective surface above the field, very low cost screen, and screen is made in such a way that you can allow the crops to get rainwater, air, sunlight, everything, but it will protect only EM waves. And if it is possible to do, then that wheat field will not be affected by EM wave and its production will be reduced. And household appliance, working frequency of microwave oven, I think maximum of us has microwave oven in our house. Its operating frequency is 2.4 gigahertz. At that time of cooking, this microwave signal comes out of the microwave oven chamber, and that will be very harmful for human being who is cooking or who is in that room at the time. And previously, door of microwave oven was made of traditional glass, so harmful effect was there. Presently, the door of microwave oven is made of frequency selective surface. This cannot radiate, this protects or reflects 2.4 gigahertz and it cannot allow that microwave signal to go out, so harmful effects reduced. In residential areas, generally in our residences, window screens may be made of frequency selective surfaces, which will not allow to enter electromagnetic radiation of high strength at the time of relaxing or sleeping. When you are sleeping, if you use window screens of surfaces, EM will not enter your room, you will be protected. At busy time, window screens made of FSS may be removed so that EM radiation can help you to operate mobile phones. Thus, this may also minimize the harmful effect of electromagnetic radiation. And now few examples or protective measures regarding biohazards waste treatment. Different sources of waste production, that may be from household, industries, factories, agriculture fields, hospital, clinics, vehicles, like this. And use of microwave in waste treatment, generally microwave frequency range is 3 to 30 gigahertz. Wastes are collected and transmuted to microwave chamber. Internal heating of wastes are done, and it can destroy spores of E. coli, like these bacteria and other harmful bios at the frequency of 2.4 gigahertz. And it can also decompose plastics and polythene. But the problem is that at this time of decomposition, at the time of destroying these biohazardous bios or materials, EM wave will be radiated to the environment, and that is harmful. Now, FSS-based waste treatment chamber are being manufactured, and this FSS-based waste treatment, whenever it is used, microwave radiation cannot go out of the environment, cannot go to the environment from this chamber. And this will also minimize the harmful effect of electromagnetic radiation. That means if we want to take necessary measures to lower the harmful effects of electromagnetic radiation, we shall have to use frequency selective surface. And what is its versatility? FSS can be, that is frequency selective surface, can be designed or it can be modified as per the requirements of the human being. It is possible to fabricate it using metal sheets. It can be possible to fabricate using metal films, transparent glass, flexible sheets, etc. The designer may also select frequency band to pass or reflect or absorb it. It is also possible for a designer to design absorber type FSS. The possible combination is extremely large. Each combination shall address different problems. Ongoing research work in the field of FSS has ushered in a new hope for solution to manage the radiation not only from the cell towers but also from other sources. So the two parts have been completed. Now, regarding the design procedure of the frequency selective surface. Before that, you should know what is frequency selective surface. In communication engineering, filter is one of the fundamental and useful circuits. Generally in low frequency, these are used in wired circuits. But in microwave communication, wireless counterpart of a wired filter is a frequency selective surface. FSS is a two-dimensional periodic array of patches on a dielectric slab or a two-dimensional array of apertures within a metallic screen. Say, this black portion is metal and white portion is dielectric slab. There is two-dimension arrays of metallic patches on a dielectric substrate. This is the general formation of frequency selective surface. that black portion, that is metallic patch, may be of different types. It may be circular, it may be square, it may be rectangular, it may be Jerusalem cross, it may be cross type, it may be dipole type, and that geometrical figure may be modified also. Now, what are the applications of this? It is commonly used in the door of microwave oven, as explaining earlier. That is the use of the household type. It is used in satellites as dichroic filter. I am explaining later. It may be used in radome for protecting the radars also. It is another use of frequency selective surface other than to protect from harmful effects of EM wave. Previously, in the satellites, suppose from ground station, two band of waves are being transmitted, X band and S band. Previously, two reflectors are used in the satellite to receive these two band of frequencies, that is X and S. Say this main reflector is installed in a satellite, and X and S band, in upper portion X band is shown and in lower portion S band is shown. Then these two bands are being transmitted from Earth station. Say X band is being reflected from this main reflector, S band is also being reflected from the main reflector. Then X band and S band both goes to the sub-reflector. This sub-reflector is designed in such a way that it can transmit S band, it can reflect X band. So S band comes to the main reflector, goes to the sub-reflector, and after transmitting it, it goes to the field. And X band from Earth station, it comes to the satellite main reflector, comes to the sub-reflector. It is being reflected from it and comes to another feed, X band feed. So X band and S band are being separated by sub-reflector manufactured by frequency selective surface, and its weight is very less. It may be around 50 gram only. So previously two main reflectors are used. One reflector means around 20 kg. So for two bands, previously there was the requirement of 20 kg into 2, that is 40 kg main reflector. Now 120 kg reflector will do the dual purposes. Only 50 gram sub-reflector of FSS is used. So if four band of frequencies are used, previously 4 reflectors are used, now only one reflector can meet the problem with some designs of frequency selective surface. As a result, the result is that tremendous decrease of the weight of the satellite. And what will be the benefit? Longevity of the satellite becomes more and more. Another application, ground-based radome where FSS is used. This radome is used by FSS. Say, here is a radar, inside it here is a radar, and radar is being communicated with a plane. If the plane is known to me, I can use a frequency which can transmit through this radome. And for enemy plane, its frequency from the plane will be absorbed. Whenever it absorbs the frequency of another plane, that plane cannot detect that here is a radar. So there is less chance to destroy the radar by the enemy. So this is also called stealth technology of the FSS. And this is microwave oven. You know that previously that door was used by that door was manufactured by glass, but presently that glass is being manufactured by frequency selective surface. What is the benefit? The cooking frequency will be inside it. It cannot come out of the screen to the environment. So there will be no harmful effect for the persons who are in this house. Now, regarding this, some designs of frequency selective surface. So frequency selective surface, what is its main application? Main application is number one, to protect from harmful effects of electromagnetic radiation. Number two, stealth technology. Number three, it increases the longevity of satellite. It has also several applications. I'm not going into detail. I'm citing some design examples. Here, this geometrical shape is called dipole. There are two-dimensional dipole arrays. Black color is metal and white color is dielectric slab. So here is two-dimensional metallic patches, array of two-dimensional metallic patches on a dielectric substrate, and its frequency response is like this. In x-axis there is frequency and y-axis there is transmitted electric field. You can see that from 6 to 7.5 gigahertz or from 8 to 10 gigahertz, all the signals are being transmitted, and frequencies around 8 gigahertz, it is being reflected. So it can reflect only a certain band of frequencies, and other frequencies will be transmitted through it. And it is just complement type frequency selective surface. This is just complementary of previous. Previously, there are arrays of metals on a dielectric slab, and here metal in position of metal there is dielectric, and in position of dielectric there are metals. That black portion is metal. And from this metallic portion, some geometrical figure like metals have been removed. This is called slots or apertures. So there are two-dimensional apertures within a metallic screen, and its response will be just reverse. Here, some frequencies is being transmitted at around 8 gigahertz, and other frequencies are being reflected. So it acts like a band pass filter, and previously it acts like a band stop filter. It acts like a band stop filter. It acts like a band pass filter. Now our requirement may be different. We may need, say, greater bandwidth. We may need left shift of right shift of pass band or stop band. For this, I am showing some designs. This is just like a square patch, and two slots are introduced there. And this is the array of patches. Patches means modified patches. Its response is like this. What is the modification? Here bandwidth has been much more. Bandwidth is around 2 gigahertz. I think, yes, 6.5 to 9. More than 2.5 gigahertz. And previously bandwidth was several megahertz. So bandwidth is being enhanced by introducing slots in the elements of the frequency selective surface. Another example I am showing. This is just ring type elements, and inside it there is a circular patch. What is its advantage? Its advantage is that, say, if this type of frequency selective surface is used, if you rotate it just 90 degree, it will not work, because in that case your position will be changed. That is, there it is vertical dipole. If it rotates 90 degree, that will be horizontal patch, so it will not work. But if your design is like that, if you rotate it 90 degree, it will not affect the frequency response, as it is symmetric from all directions. So different dimensions, different figures, different polarization independent field, these are being designed for various purposes. And these are the basic designs of frequency selective surfaces. I am not going into detail about its mathematical formulation, but you can use the previous softwares for analysis which are being used in antenna also, that is MOM, FDDT, FEM, etc. And also you can use fabrication technique also, and its frequency response is like this. That's all about the presentation. You may ask question.
Okay, participants, I am requesting to all the participants, if have you any queries regarding this presentation, which is delivered by Dr. Parthopratim Sarkar, please you may ask.
Good morning, sir.
Sir, Sir Parthopratim Sarkar.
Yes. Can you hear me?
Sir, if possible, sir, please on your camera, sir, if possible.
Okay. I'm trying to make on my camera.
Good morning, sir.
Yes.
Sir, very good morning, sir, respected sir. And I have a question. That, sir, what is the difference between the metamaterial and FSS? Because in some papers they are using metamaterials and they are also using the FSS to fulfill the various heat of the patch antenna. So, what are the basic difference between these two values, that is FSS and metamaterial? That is my question.
Yes, I am explaining. Generally, I have explained here all the FSS structures which are being manufactured by normal material. Normal material means its epsilon is greater than 0 and mu is greater than 0. That is, permittivity and permeability both are greater than 0. These are the normal materials. And physically, you can say that group velocity and phase velocity both are in positive direction. But metamaterial is a material which is different from the normal material. Some properties are being as if designed in the metamaterial. There, epsilon and mu both are made negative. It is very difficult, but it is made negative. If you use metamaterial to design FSS, its compactness may be more. If you use metamaterial to design a microstrip antenna, its compactness may be more. I am giving you one example. Say, you want to design a microstrip antenna without any modification. Say, its dimension will be around the half of the wavelength, lambda by 2. If you try to make it compact by slot introduction, by other thing, then say wavelength may be minimally lambda by 10, lambda by 12, lambda by 15, etc. If you use metamaterial and then you want to modify, it may reduce it up to lambda by 50. So metamaterial is totally different thing, but that material is being used in FSS design and FSS design also. But in that case, we shall have to consider the commercial aspect also. Whenever you use metamaterial and you want to modify the designs, then your needs and cost, that should be considered. I think you understand my point.
Yes, sir. Yes, sir. Thank you, sir.
Any more question?
Hello, good morning, sir.
Yes.
Sir, I have a question. If FSS is present in mobile phone, sir, we heard that FSS is present in mobile phone to filter out the radiation, harmful radiation from the mobile phone. So how much it can be filtered out, or how much it can be prevented from the mobile phone, sir, by FSS?
One thing maybe, say you are using your mobile phone. Whenever your mobile phone is switched off, still there is several EM waves that may be of frequency of mobile signal, that may be frequency of Wi-Fi, that may be frequency of others. Only when you switch on your mobile, the mobile signal is being amplified. So always, other than your mobile signal frequency, there are at least 12 to 15 types of other EM waves also around your mobile. If you use your FSS, there will be less chance of that signals to be amplified. Only your mobile signals will enter your mobile phone, that will be amplified, and that will be in your operating stage. So FSS screen may be used in mobile phone, but that should allow mobile signal frequency to enter the mobile and to reflect or to absorb other signal frequencies. In that case, EM radiation will be reduced, but not it will be zero. Understand my point?
Understand, sir.
Anybody of you, don't hesitate to ask any question. If there is any question in your mind, you are free to ask.
Hello,
yes.
sir. Myself Deepak.
Yes, I can.
I want to ask that, sir, when we consider the bandwidth consideration, we always take less than minus 10 decibel. Where you explain that 90% is transmitted, 10% is reflected for the
Okay,
consideration.
I am explaining.
But how is here? How mathematically we can prove that 90% is transmitted, 10% is reflected?
I am trying to explain. If it is not clear, please repeat again. Okay. I am trying to explain. If it is not clear to you, please repeat again.
Okay,
say minus 10 dB means 1 by 10. Minus 20 dB means 1 by 100. Say you are plotting reflection coefficient versus frequency. Reflection coefficient versus frequency. Reflection coefficient means reflected field divided by incident field. Say 10 watt is incident and 2 watt is reflected. So what will be the reflection coefficient? 2 by 10, that is 1 by 5. Say 10 watt is fed, that is incident, 1 watt is reflected. 1 watt is reflected means 9 watt will be transmitted. So what will be the reflection coefficient? 1 by 10. Say 10 watt is fed, half is reflected and 9.5 is transmitted. So what is the reflection coefficient? Half divided by 10, that means 1 by 20. Say whenever you are plotting reflection coefficient versus frequency, 1 to 5 gigahertz, it is minus 5 decibel. 5 to 6, minus 12 or minus 10, less than minus 10. At 6, it is minus 8 or minus 7. So if you start from 1 gigahertz to 20 gigahertz, say only in 5 gigahertz to 6 gigahertz, reflection coefficient is below minus 10 decibel. Below minus 10 decibel means it is less than 1 by 10. Reflection is less than 1 by 10. Reflection is 1 by 10 means if x watt power is fed, x by 10 power is reflected back and 9x by 10 power is radiated. So whenever the frequency in the frequency band where reflection coefficient will be less than minus 10 decibel, in that band reflected field of course will be less than 10% of incident field and radiation will be greater than 90%. If you don't understand, repeat. I am again explaining.
Sir, understand, sir.
Okay.
Sir, I have a question.
Of course.
What are the main differences between the normal filter and the FSS? What would happen if we use normal filter instead of FSS?
Normal
filter
and FSS. Okay. Normal filter is generally working in several up to megahertz, not above. Normal filter means there will be an L, there will be an C, there will be some wire. Say dimension of inductor, dimension of capacitor, dimension of wire. Generally, they are of the order of wavelength microwave signal. Whenever anything will be in the order of the wavelength of the signal, there may be resonance, there may be interference. So wired circuits cannot be used in microwave signals as wavelength of microwave signals is around centimeter and inductor, capacitor, wire, their dimensions are of the order of centimeter. So there may be interference, there may be resonance. This is that capacitors, inductors are not generally used in microwave circuits. Understand?
Okay, sir. Thank you, sir.
Any questions?
Don't hesitate to ask any question.
Hello, sir. Hello.
I can't hear. Please tell me.
Hello, sir. My name is Sunil Chandra, sir. Sir, can you please tell me about some polarization in sensitive frequency selective sources?
Of course. Yes. I think you have a clear idea about electrical polarization. First, I am saying, say a wave is going towards x direction and magnetic field is in y direction and electric field is in z direction. Then it is polarized in z direction. Say wave is going on, electric field is parallel to horizontal, then it is called horizontally polarized. Say electric field is in the plane of vertical, it will be called vertically polarized. Say the electric field is in two directions, in x direction and y direction. But their equation is like that. In x direction it is a sine theta and in y direction it is also a sine theta. Then the polarization will be linear. But say in x direction it is a sine theta and in y direction it is a cos theta. Then what will be the difference? say theta equal to 0 degree, then value of electric field in x and y direction, this will be a and 0. If it is 45 degree, it will be a by root 2, a by root 2. If it is 90 degree, it will be 0a. That is, from origin, always its distance is a. Then it is called circularly polarized. And in case of FSS, say a wave is vertically polarized, and FSS is designed to cope it, to tackle it for vertical polarization. If you rotate the FSS 90 degree, it will not work again. But in my slide, in the last figure, where there is circular ring, if you rotate it 90 degree, 30 degree, 20 degree, its dimension, its geometrical figure will remain always same. So if polarization changes from vertical to horizontal, that will not be affected, that FSS will not be affected. But in case of, say, vertical dipole or horizontal dipole, if polarization changes, that FSS will not work. This is the basic concept of polarization and its relation with FSS.
Thank you, sir.
It is clear?
Clear, sir. Thank you, sir.
Any more question? Achha, one thing I want to ask, is it clear to you, the presentation? What I presented, has it been clear? I know that it is not possible to be clear 100%, at least 40 to 50%. Is it clear?
Yes, sir. Yes, sir.
Yes,
It was
sir.
very
Yes, sir.
clear, sir.
Sir.
Okay.
We want the presentation. Can you share the presentation so that we can revise it?
Okay. Now, from your part, any more question?
Sir, I already asked one question. I want to repeat this question, that why we take that minus 10 dB as a reference line.
Please, I can't hear. Please repeat.
I already asked that question, that for the bandwidth consideration, 90% transmitted, 10% reflected, considered as minus 10 decibel.
Yes.
But sir, why we take that support 10 watt is transmitted, we 1 watt is reflected, we consider that. Why we consider that 1 watt reflected? Why not 100%?
Why not 5%? You are asking why it is 10%, why it is not 2%, why it is not 1%, is it?
Yes, sir.
Yes. Generally, whenever you design amplifier, in low frequency amplifier, I think you know that we consider 3 dB bandwidth. Clear?
Yes, sir.
3 dB means half power bandwidth. But in case of antenna, if 20% power is reflected back and 80% power is radiated, then 20% loss of power means heavy loss of power. Because to generate microwave power, generation of microwave power is heavy costly. So internationally we have accepted 10% loss may be accepted. More than 10% loss should not be accepted. Generally we consider more than 90% radiation, 95, 96, 97, like that. But if it goes below 90%, radiation goes below 90%, that is reflection becomes more than 10%, the design is totally rejected. We try our best to make it 95%, not 90%, but 90% is the threshold after discussion of several international bodies. In low frequency, it is half, but in case of microwave, it is considered 1/10. That is the power, but we try to make it 95 to 99%. I don't know whether it is clear.
Sir, it is clear somehow. Sir, can I ask question from that for the circular polarization,
From anywhere.
we
You
consider
may ask.
circular polarization we consider as a 3 decibel for the it is circular polarization, linear polarization. What you have said in the previous question.
What is you want to know what is circular polarization, or you want to know what is the usefulness of circular polarization?
How can you differentiate the circular polarization and linear polarization?
Understand.
In a decibel gain point of view.
Yes. I think you know about a term axial ratio.
Yes,
I
sir,
think
actually.
if the axial ratio of an antenna in the frequency range where axial ratio will be less than 3 dB, that portion is called circularly polarized. And where axial ratio goes beyond 3 dB, that is 5, 4, 6, 7, 8, that is not called circularly polarized.
Yes, sir.
An advantage of circular polarization is that there is both horizontal and vertical polarization. That means more channels may be accommodated. And also, if it is there is some change of polarization, some shift of satellite, say antenna, there will be no effect. There will be no effect on the shift of antenna regarding power transmission or reception. Any more questions?
Any more questions? Okay, I think, sir, there is no more question is there. So, from the participant point of view, sir, I am requesting to you, sir, please, if possible, share your presentation. So it will be helpful for our participants.
In that case, I am sending the slides to you. Is it possible to share?
Or if you share through mail, also I can share it to our participants. Because
No, I have no mail ID of the participants at this moment.
No problem, sir. You can share it with me. Then all the participants' email ID is given to me. So then I will share it. No problem.
So I am sending the total PPT to you.
Okay, sir. Okay.
I am sending the total PPT to you, and please send the PPT to all the participants.
Okay, sir. Okay. That will be better, sir. Thank you, sir. Once again.
Thank you to all participants for their patient sharing. Thank to all participants. I don't know how many participants are there.
Right now, sir, 119 participants are joining right now. So actually, the total maximum number of participants is 200.
Okay.
So,
And Fulan, one thing, please share my email to them also. If they have any query, they may mail me directly also. No problem.
okay, sir. Just wait, sir. I am in chat box. I am sharing your email ID.
And I shall send within 5 minutes. I shall send the PPT to you.
Okay, sir. PATHA. No, sorry. PARTHABE91 @yahoo.com. Right, sir?
No, yahoo.co.in.
Okay. Yahoo.co.in. PARTHABE91 @yahoo.co.in.
Yes.
Okay, sir. I am sharing it to our participants so that they can direct contact with you if they are facing any problem regarding this.
And PPT, you will please send it to all the participants. I am sending you within 5 minutes.
Yes, sir. So once again, I would like to thanks to Dr. Parthaputim Sarkar for deliver his valuable lecture and the practical point of view and in the field of microwave, especially antenna and FSS. and the present applications of the FSS and antenna for the wireless communication system. So as a coordinator of this faculty development program, so I would like to convey my special thanks to Dr. Parthabatim Sarkar. Thank you, sir. Thank you very much.
Thank you to all.
Thank
May I-
thank you, sir.
Thank you, sir.
Thank you, sir. Thank you very much for this.
Thank you, sir. Organizers. Thanks to all.
Thanks for your presentation. Nice presentation, sir. Thank you.
Thank you.
Thank you. Thank you. So I am leaving.
Okay, sir. Okay. Thank you, sir. Okay.
Hello, sir.
Sir, is there any attendance link? Is
No,
there any attendance?
attendance sheet, we will provide the attendance sheet later, not right now. Okay. And also automatically attendance is collected in our software.
Okay, sir. Okay, sir.
Okay. And later we will share a Google form also, so you can provide your attendance through this. Okay.
Okay, sir.
So,
Okay.
so now we are taking short break. We next session start
1:30.
at the time of 1:25 p.m. So please stay with us. So after a short break, we will start our next session. Okay.
Thank you, sir.
Okay, sir.
Thank you, sir.
Thank you.
sir.
चला चला माझ्याकडे भाजी नाही आज त्यामुळे मला येणं भाग आहे. चलो. अरे खूपच खराब झालाय आवाज काय.
से डे वाइज हाँ सियोर ମୁଁ ପଠେଇବି ଆପଣ ହଁ କୋଉଠି actually ସେ OMS ରେ total real time attendance ଆସୁଛି real time attendance ସବୁ ପିଲା ବି 100% କାର ଆସି Google Sheet ନବା 200 ପିଲା କରୁଛନ୍ତି 40ଟା ପିଲାକୁ ସେଥିପାଇଁ ଡେ ୱାଇଜ କରାଇଛି OMS ରେ ପୁରା attendance ହେଇକି Excel sheet ପଳେଇ ଯାଉଛି ଆପଣ OMS ଖାଲି ଯେତେବେଳେ ଚାହୁଁଛନ୍ତି ଅନ୍ ଟେ କରିଦେଇ Google Sheet 4ଟା ବେଳେ ପଠେଇବି 11:04 କୋଉ ହସ୍ପିଟାଲ କଣ କିଛି ନୂଆ ଖବର କି ଏମିତି ମାନେ କଣ କହୁନ ଆରେ ସେଟା ତମେ ଏତେ ବାଟ ଆଗେଇ ଗଲାଣି ମତେ କହିନା କୋଉଠି ଏମକେସିରେ ଖ୍ରୀଷ୍ଟିଆନରେ କାହିଁ ଗଲ ଏମକେସି ଗଲନି ଭଲ ଖ୍ରୀଷ୍ଟିଆନ ବି ଗଭର୍ଣ୍ଣମେଣ୍ଟ ଏଇଟା ବି ଗଭର୍ଣ୍ଣମେଣ୍ଟ ତମକୁ ଏବେ ଲିଙ୍କ ପଠେଇ ଦଉଛି, ତମେ 4ଟା ବେଳକୁ ଦବ ତ ଆଟେଣ୍ଡାନ୍ସ ଟା, ଟାଇମିଂ ରେ 4ଟା ବେଳକୁ ପଠେଇ ପଡିବ।
Kalyan sir, please send attendance link. Good afternoon. You are mute. You are muted. Unmute yourself. Am I audible? Okay. Actually, you are muted. I could not.
You are audible. Okay. So, just we would like to start our second session, day 1 in faculty development program. The title of the faculty development program is the trends of research and development of electronics and communication area from 17th January to 21st January 2022. So, once again, Happy New Year to all the participants and experts. Happy New Year. So thank you, sir. So sponsored by AICT Training and Learning ATAL Academy and organized by Department of Electronics and Communication Engineering, NIT Manipur. So I am coordinator Dr. Kullan Mondol. So we would like to start our second session. So with the permission of our expert.
Yeah, sure. Yeah.
Okay. Just I over to you, mic to Madam Onupa, Madam, please. Madam, are you available? Madam, hello. Just a minute, sir.
So till that time, I am trying to share my screen. Let's see.
Madam Rupa, I am audible?
Is my screen visible?
Yes, sir. Yes, sir. You are visible, sir.
Hello? Am I audible?
Yes, ma'am.
Audible. Yes, ma'am.
Yes, ma'am. Yes, ma'am. You are
Okay,
audible.
okay. Sorry, there was some problem on my side. That's why I was not able to join. Okay. First of all, before continuing the technical session, let me give a brief introduction of the speaker. We have with us Dr. Somawa Mukherjee, Assistant Professor, Electrical Engineering, IIT Jodhpur, to talk on application of substrate integrated circuits in microwave and millimeter wave frequencies. Somawa Mukherjee was born in Kolkata, West Bengal, India, in May 1987. He received the BTech degree in Electronics and Communication Engineering from the West Bengal University of Technology in 2009, the ME degree in Electronics and Telecommunication Engineering from Bengal Engineering and Science University, Shibpur in 2011, with specialization in Microwave and Communication Engineering, and the PhD degree from the Department of Electrical Engineering, IIT Kanpur in 2016. Since 2016, he has been an assistant professor with the Electrical Engineering Department, IIT Jodhpur, India. His current research interests include substrate integrated coaxial line antennas and circuits, substrate integrated waveguide antennas, multi-frequency and broadband antennas, and chipless RFID. Dr. Mukherjee was a recipient of the European Microwave Student Grant in EUMC 2013 and EUMC 2014. He also received the International Travel Grant from the Department of Science and Technology, Government of India. He is also a recipient of the Young Scientist Award APRASC 2019, instituted by the International Union of Radio Science. He is also a reviewer of potential journals like IEEE Transactions on Antennas and Propagation, the IEEE Antenna Wireless Propagation Letters, IEEE Access, IET Microwaves, Antennas and Propagation, UK IET Electronics Letter, UK and IET Journals of Engineering, UK. Over to you, sir.
Thank you. Am I audible clearly?
Yes, sir.
Yes, sir. You are audible.
Thank you very much for this nice introduction, and thank you for inviting me in this faculty development program. So if it was a physical session, then I would have the opportunity to come to NIT Monipur. I think it's a new campus, and I would love to visit that campus. But anyway, right now it was not possible. So yeah, so let me start. I think my screen is visible. So this is my topic: substrate integrated circuits, microwave and millimeter wave applications. And so unfortunately the laser I could not see here, probably some issue. So this arrow I will use instead. Okay. So let me start my talk. So before I go into the detail of this substrate integrated circuits, let me little bit talk about my institute. So this is a very brief background of how my institute looks right now. This is the IIT Jodhpur main administrative building, which you will see once you enter the campus. And then after that, there is a library and the clock tower, which is one of the major iconic building, you can say. After that, other buildings are there. And yeah, here is the director's bungalow and all those other things. So basically, we are here in this part of the country in Jodhpur, Rajasthan, and typically this is how is the view of the Jodhpur, and that's why you can see this is the famous Mehrangarh Fort, and from the fort you will see that buildings are all blue. That's why it is called Blue City. It is also called Sun City because of the most of the time of the year you will get very good exposure of sun. So talking about our institute, it is established in 2008. Right now we have 1,700 students, 200 faculty members, 12 department and 7 interdisciplinary research platform. In talking about my department, it is having currently 2 MTech programs along with the BTech electrical engineering program. When the 2 programs are on SIoT and CPS. There are dual degree programs of MTech PhD as well, and also PhD program in different areas of electrical engineering. So also in our BTech program, there are many other options available, which is typically available in many of the eminent institutes in the country. So these are some glimpses of the institute. This is the lecture hall building, and this is the day of the convocation it was taken. These are some of the architecture, you can say, which was recently installed in our institute. This is just a brief idea about the institute. So after that, now I will start my discussion. So I'll briefly talk about the microwave and millimeter wave applications, whatever we are going to use and which we are using right now. Then I'll talk about the substrate integrated circuits, especially the 2 technology, substrate integrated waveguide technology and in substrate integrated coaxial line technology. And we will see as far as our time permits and whatever is possible, I'll try to cover, and then I'll finish the talk. So let me start with this microwave and millimeter wave. So basically, this is a brief idea you can say about the frequency and the wavelength. So here you can see the frequency is increasing gradually, and as we all know that the wavelength is actually inversely proportional to wavelength is decreasing. So basically, in the kilohertz range here, your wavelength is around the tall buildings. That much big wavelength is there. As you move to the megahertz, then your wavelength becomes the height of the human. But then as you move to the microwave, that means 10 to the 9 gigahertz range, there your wavelength becomes in centimeters. So it is almost in the size of the butterfly. And then as you move more than that, then after 30 gigahertz, it comes to the millimeter wave region, which extends up to 100 gigahertz, and after that the terahertz region starts. So terahertz is actually a region from where this some of the photonic applications are also coming into the picture. Ultimately, it goes to infrared, visible light, UV, X-ray, and gamma rays. And as you can see, the wavelength becomes very, very small up to the molecular level and atomic level. So actually, from this visible light, there is this dual nature of wave and particles comes into the picture, and that's why there the physics becomes a little bit different. You cannot use the same theory which you can use here, you cannot apply that here. And typically from here to here, you can apply to some extent this similar theory, and we will be restricting majorly in this portion only in today's discussion. So basically, all terrestrial communications typically will be point-to-point communication, which is of line of sight into the visual horizon. But we have different technologies to overcome that limitation, which we all probably have known so far. But talking about the millimeter wave at the higher end of the band, there is a atmospheric absorption also coming into the picture. So those are some challenges which right now people are thinking about how to overcome, and some of them I will try to discuss in today's talk. So this figure I'm just showing just to have an idea that how gradually the technology has progressed. So this left figure, what you are seeing, was used in World War One. So at that time, waveguide was the most prominent technology, and this was a complete radar system which they used to carry in the aircraft. You can see that how heavy it is. It is a total transceiver system. That means transmitting, emission, and receiving. All those things are done in the same system, and everything was very bulky, heavyweight waveguide structure. Now, from there, we have today come to here, which is the right one is actually satellite dish TV receiver, which we typically use in nowadays in all the households. So basically, here is the antenna which you will connect, and the two ports are, one is transmitting and one is receiving. As you can see that in both the cases, there is a microstrip based filter, then there are amplifier and mixer and all those components are there. After that, there is this baseband circuitry also is visible. So this is very bulky. This is very much lightweight, and probably you can means right now we have this capability to make it much more smaller so that you can carry it in your pocket, the one you are using as a mobile phone. So we have come from here to here. Okay, and this happened because of the invention of this technology, microstrip technology, and also the advancement of the solid state devices, which we could not use here. Here it was majorly those these vacuum tube devices that time people used to do, which was replaced by these solid state devices, and ultimately we could make it a complete package, very compact form. So the advancement you can see is very rapid and very exciting to see, and as you can see from here to here. But then the question comes, what's next? Now what? Where actually we are going? So I'll just briefly try to show you those things. Before I'm going there, I'll just show you this brief idea about how the applications are going. Yes, is there any problem? Okay. So I'm just showing some brief idea about the different frequency ranges, what are the applications. So starting from the AM broadcast, which is in kilohertz, you can see that FM radio, which you are all listening, and they all tell about the channel. So these are in this range, 88 to 108 megahertz. And then eventually we reach to the 900 megahertz, and ultimately 1.575 is the GPS, and 2.45 is industrial, scientific, and medical application, 2.45 gigahertz, ISM band, and so on. Okay, UWB is up to 10.6 gigahertz. So basically, as I said, that these all to some extent can be used with the similar concept, but as the frequencies are changing, the wavelengths are changing, so a little bit difference in the engineering comes into the picture. And typically, the standard convention is that to name these frequency bands with this type of letter. So I'm not sure how many of you actually know that. So basically, mostly we use these regions from 1 to 40, and then these are the naming LS, CX, and KU, K, and K band. Mostly nowadays, whatever households you are using of microwave application lies in this L to C band only. X band typically right now is being used for the defense application. Even the KU, K, and KA band are not explored much, but now people are starting to use them, starting to think about how to use those bands, which are not so far has been used for commercial purpose. And also people are moving ahead. They are going beyond 40 gigahertz. So this U, V, E, W, and F band are also coming into the picture. So up to 140 gigahertz is, as I said, you can still apply this same physics. After that, the terahertz region, you have to also think about the photonic concept as well. So these are the scenario right now. Right now we are using up to here, but then as you are moving ahead, you have to deal with certain things. Like I said, that at the start of this region, there is the absorption of the atmosphere comes into the picture. So you have to deal with that. As you move further ahead, the photonic concept comes into the picture. But you may think that why I need to go there? The one which we are using, what is the problem? The problem is, I'll tell you, but before that, let me show you some of the applications which you are using right now. So right now, as I said, L, S, and C band, we are typically using this type of application like point-to-point communication. If you move around along your this area, you will see that many buildings typically where these internet service providers have installed their equipments, you will see that these antennas are there, which are actually for the point-to-point communication from one node to another node. So typically, it will look like this in either city or in the township. Typically, you will find. Then there are Wi-Fi router wireless networks. So almost all of us are using that. There are this microwave radio relay network in the mobile base station. So these all types of antennas which are actually communicating between multiple towers. There are automotive application for collision avoidance radar application, and these door openers. And many of you have seen that automatically the door opens. Basically, this is nothing but a Doppler radar. So inside it, there will be a microwave range antenna, and that actually detects the Doppler shift when you are coming to the door. And detecting that shift, it will indicate that, okay, you are coming, so it can open the door. And also microwave oven, many of us are using right now. So that is also in the micro frequency range. And most important one is this mobile communication, which is right now we are at 4G, starting from 1G. So what is the difference between them in these applications? So if I just try to show you, these are a long table. I'll just focus on some certain points of those different generation. So first one is the speed. As you can see that as the generation is increasing, the speed of the communication, this data transfer is actually increasing day by day. And right now we are at the 100 of Mbps level, even somewhat more than that also. And as the speed is increasing, your bandwidth is also needs to be increased. So first generation had no internet access, and gradually we have reached up to ultra broadband internet access. But and along with that also we have the other technological differences as well, which I'm discussing right now. We will be focusing on this here. And as you all know, we are actually now in a point where we are moving from 4G to 5G. So what is the difference in the 5G? So 5G actually is what people typically saying is a paradigm shift. So basically it has three pillars, major pillars, which you can see here. One is enhanced mobile broadband, which is more related to the commercial application or consumer application, I should say. So basically this is responsible for this concept that in 3G it was in kbps, download and upload speed. In 4G it was 100 Mbps. 5G it will be 10 Gbps and more than that. So of course, better download speed, better bandwidth, everything. So this is all related to this enhanced mobile broadband concept. There is other two pillars as well. One is massive machine-to-machine communication, which is more related to the IoT-based application, and ultra reliable and low latency application, which is more related to specifically industrial IoT or Industry 4.0 application. So basically 5G is not only the enhancement of the consumer forum as well as the industry, and definitely it's a paradigm shift if it can give all these three pillars. So just to give you a brief idea that what exactly the world will look like if the 5G can deliver these things. Of course, this requires, there are certain challenges, like as you can understand from this concept, is that you need to actually improve your hardware much more than that. So it requires investment, and that is definitely a challenge to the service provider as well as the consumer. They have to also buy it. So those challenges are there. But if it can be provided, then we will be looking to the world in the new. For example, this figure is actually giving you a idea of that. Here, what it is showing is that a factory, the complete factory, can be controlled sitting in a control room because everything is connected. And these are typically talking about ultra reliable, low latency. So once you switch the button, low latency typically means that once you press the button and that signal is going to the machine, and then that machine is started working. But what is the delay between that? So in 5G, that delay will be much lesser than 4G, and therefore actually you can be able to control the complete factory sitting in a control room. So that is industry automation. Okay. Next one is the automatic farming. The controlling a tractor sitting in a control room. You actually don't need to go to the farm to do that. You can, talking to the enhanced mobile broadband, you can communicate from the moving aeroplane. You can communicate from the moving cars. There will be car-to-car communication, that is vehicular communication application, even with car to building, and everything is connected there. You can talk about this machine-to-machine communication, and IoT application will be one example is hospital, where all the medical inventory, all the patient information, everything is connected, and doctor can see to that. Yes. Hello. Am I audible?
Yes, sir. Yes, sir.
Okay. Okay. So all this hospital and everything is connected. You can think about even this enhanced mobile broadband application can be this AR and VR application, where people sitting in their home itself can actually get their AR headset, augmented reality headset, and do multiple type of thing. AR headset not only for the gaming, maybe different application as well, which is actual work from home type of situation can arise. So all these things, all these. So as you can see, if actually 5G can be delivered, you will be actually seeing the world in a different way, which we cannot imagine right now. Actually, we have seen a paradigm shift even with 4G, as you can see. Even certain days ago, we have no idea that we can use our mobile phone for payment. But nowadays, it is all thanks to this UPI, some Beam application, you can do it. So that's a paradigm shift. But yes, so the next paradigm shift also can come if the 5G can be delivered. So I'll just show you some brief example of what it can deliver. So this is actually a photo taken when I went for a conference in Japan. So basically, Japan had a plan to demonstrate this start their 5G communication with the 2020 Olympic, Tokyo Olympic, which didn't happen because of the COVID. But when I went, they were actually displaying those technologies. It was by NTT Docomo. So they had these two frequencies with them. One was this sub-6 gigahertz, and one was at millimeter. Both the antennas they have made, and they were showing them. And they were also showing some application. Like right now, probably if you go to the this any electronics market, you will see 4K video. They were showing that 8K video will be possible with the 5G application. They were showing that sitting in the control room and trying to control these tractors in a mine, so they don't actually have to go there. There is no effect of pollution with the body and all those things they were showing. So these all are promises, and these all people are trying to demonstrate. Some of them has demonstrated. Even in India also, these are coming in a big way. Maybe end of this year, you will start seeing these type of things. So definitely the industry also going to be changed a lot, as well as your daily activities as well. So as I have said, that the bandwidth has to be increased for this 5G application, as well as the this other things are there. So how to do that? So basically the challenge is that, as I have shown you in the lower region, your total band is actually very much congested with our daily basis applications. So increasing the bandwidth there is a lot of challenge. I'm not saying that it is not possible. Yes, people are trying with different applications, like MIMO technologies are there. Massive MIMO is coming. these technologies are also very promising. Along with that, there is a chance that we can move to the millimeter wave, which has not been explored yet. So a big chunk of bandwidth is available to us without any use right now. So people can move there as well. So 5G has, that's why 5G, whenever they started with two bands. One was sub 6, means below 6 gigahertz. One was 8 millimeter. Now, talking to the millimeter wave, how to actually make a millimeter wave system, there is a different challenge. So challenge is to show that comparison. I am just showing this figure. So the left hand side, what you are seeing is a 2.4 gigahertz transceiver system, which can be as small as possible that you can put in your pocket. So basically, this is your antenna, which is PFA antenna. And after that, all these are this is a semiconductor device which can convert it into the baseband, and then the conventional baseband circuit can be used, and it can be very compact form. And that is possible due to this microstrip based technology, which you can use extensively in any substrate depending on the design specifications. But once you go to the millimeter wave, the typical transceiver system still looks like this. So basically, millimeter wave systems, even up to certain, even 2-3 years back, people were only relying on the waveguide based system. So basically, we are stuck with this waveguide based heavy, bulky system with very big antennas, and definitely this cannot be fit in your pocket, right? So, but our daily consumer application needs that. So we cannot use this for our daily consumer application, right? So how to do that? That's the challenge. And another challenge is that if you are using this waveguide based system, then how you are actually going to integrate with the semiconductor devices. For example, if you want to actually do it, it will be something like that. So this is a waveguide based system which are trying to be communicated with this semiconductor based PCB, and there has to be a very big and precise design of transition, and that is not very easy to make, and that actually makes the manufacturing cost higher, as well as the cost of the device accordingly becomes higher because of the skill set required for this. So that is the challenge, and today what I am going to show you is the promise which may bring down the cost to a lower end. So as I was saying, the waveguide to microstrip transition. So because all the semiconductor-based device directly cannot be put into the waveguide, because as you all know that a waveguide is a single conductor design. So installing a semiconductor device there will not be possible. So therefore you have to have a change of technology from waveguide to microstrip, or at least for those part. Why we cannot use microstrip in the millimeter wave? So the reason is because microstrip is an open structure, so it has a lot of tendency to have a radiation loss at this frequency range. So therefore, it's not very promising at those frequencies. So therefore, people prefer waveguide-based technology. Now, talking about the transition, these are very crucial transition. As you can see, this is one example. And as the millimeter wave means that we are talking about wavelength in terms of millimeter. So even a 1 millimeter can be actually in terms of lambda. So a small fabrication error of 1 millimeter can actually affect your design, because it is actually affecting multiples of lambda in those frequency ranges. So therefore, if you want to make this type of transition from microstrip to waveguide, all these dimensions has to have precision in terms of millimeter, which is very difficult to make. And ultimately, you have to make such kind of system, which is actually shown here, and it's not easy. And therefore the manufacturing cost increases. So all the system level integration becomes very difficult. So high manufacturing cost, even waveguide is the high volume, complicated transition. All these challenges makes our application of millimeter wave for the consumer electronics becomes very difficult job to do. So these are all details you can see in this paper. So what is the solution? So that's where I am starting, that what is the technology. Substrate integrated into circuits technology came into the picture even I think 10 years back, and then people started using it, and yes, it has the potential to do that. Any question? Is it okay? So basically, how it started. So the first report of this integrated circuits in a substrate was reported in 1994, when a patent, Japanese patent, was reported, and at that time it was called waveguide lines. So basically, what it was told is that if you can put rows of metallic vias in a substrate, it can be used as a waveguide-like structure. Okay, how? So the top conductor and the bottom conductor typically you will be able to find in a commercial market. If you go and buy a PCB substrate, it will have a double layer copper cladding. That means top will be covered with copper and bottom also will be covered with copper. So the top metal and bottom metal is automatically there. Now the side wall you cannot make inside the substrate, but what you can make, you can drill holes and make metallic conduction. So therefore, we will have a rows of metallic vias. So these rows of metallic vias actually can make a sidewall-like structure, and therefore the complete encapsulation of metallic encapsulation can be possible. And that's how you can make waveguide lines. So later on, then some different variation of this came into the picture, like laminated waveguide also was reported where multiple layers were given, and also some parallel plate waveguide also came into the picture. So everything, they were trying to implement those waveguide based circuit into a PCB, planar circuit board, which you can actually put in your pocket. So this was the first example where people shown that yes, we can probably try to implement those circuits in a pocket-based application. So basically, if you see the technology background, so that is what I was discussing, that waveguide-based circuits for millimeter wave technology is much more essential, but it is not suitable for low-cost mass fabrication, whereas it is bulky, so it cannot be very suitable for consumer. So there is a gap which is need to make a bridge, and that bridge came into the picture as a substrate integrated waveguide. So what is it actually, as I already explained? So basically, this is your substrate, dielectric substrate, which if you buy, you will have this top conductor and bottom conductor, and these metallic vias, rows of metallic vias, will make your side wall. So all total, you will have 4 walls of metal, and that will give you the waveguide-based behavior. So basically, it will be definitely low loss then, because it has a metallic encapsulation. So radiation loss and surface wave loss will not come into the picture. So it will be low loss. It will be high Q line. It will have better power handling capability than Microstrip. Of course, shielding is better and easy to fabricate, which was not there in case of waveguide-based application. So that's why this became a little bit popular. And this is not the only technology which became popular. So there are other type of substrate integrated circuits which also came into the picture. These all are coming from the different variation of waveguide or related technology. For example, the first one is the waveguide, which is substrate integrated waveguide, which I discussed. The second one is substrate integrated slab waveguide. So waveguide with slab waveguide we all have seen, where a dielectric slab is in between and both sides there are air. So basically here people have shown that you can make air-based vias which will actually try to implement this structure. Similarly, the sidewalls can be removed and we can get a non-radiating dielectric waveguide in a substrate integrated form. So that will be substrate integrated non-radiating dielectric waveguide. Okay. Similarly, we can have image dielectric guide, we can have inset dielectric guide, we can have insular dielectric guide. So all these forms are possible because based on these different types of metallic and non-metallic holes if you can make in a PCB. But of course, there is a challenge that of the fabrication, because typically if you make a drill, you are also drilling in the metallic part in the bottom line. So basically, making this type of structure only drill in the substrate but not in the metal is a little bit difficult to do. So that's why all these possibilities, among all these possibilities, this substrate integrated waveguide is actually most easy to make, and that's why it became most popular one, which people adopted. Okay, so yeah, I think I have discussed. Yeah, so one thing is that how to make excite this type of structure. So for that, people also found out different types of transition. transition with respect to the microstrip, transition with respect to the GCPW. Typically, they looks like that, and as you can see, they are very easy to fabricate using the conventional PCB technology, and that's why actually this became most popular one. Even considering the other type of substrate indicated circuits, there the transition is not that much simple. So this is actually very easy to simple, easy to fabricate, easy to integrate with other technologies. So that's why people loved it. Okay. So how typically it works. So the substrate integrated waveguide, if you see, it looks like this. So this is via, and then there is a gap, then again via, then there is a gap, and so on. So if you see the surface current distribution, it will look something like that, that through the via the currents will go, but in the gap there will be no current. So basically any current which is orthogonal to this gap, which cannot be propagated in the waveguide. So all waveguide modes cannot propagate in the substrate integrated waveguide. And basically we will be able to only propagate T to M0 modes only. Right. So now, so these modes are not present, but mostly whenever we are talking about waveguide, we only talk about the dominant mode TE10, which can easily propagate in the waveguide. And this is just an example. So if you see here the magnitude of electric field and the surface current distribution, it actually replicates what is there in the waveguide. That is replicated here. So basically we can make a planar PCB based waveguide circuit which actually can propagate the TE10 mode, and then we can apply all those theories which are available for dominant mode waveguide based circuits. We can directly apply it here and it will work. Actually, people have demonstrated that as well. So is it exactly waveguide? The answer is no. If you actually see the design curves which people have studied and reported, is that this is a graph of cutoff frequency with respect to the width. So we all know that this width and cutoff frequency of the waveguide is actually inversely proportional. So that we can see here. But what is interesting to see here is that if you see, if you are changing the diameter of these vias as well as the pitch of the vias, your cutoff frequency is slightly changing. So that means that is also visible whenever you are trying to make this propagation constant graph that is showing this T10 based beta curve, but with a deflection with the normal waveguide. So which it is telling is that the width of the SIW is not only a function of the this cutoff frequency or the operating frequency, but it is also a function of the diameter and pitch of the vias. So therefore, people came up with empirical formulas, closed form formulas. For, of course, it is a closed form, so it is an approximate formula. Will work in a particular range, but typically we actually make our designs within that range. So these formulas, these are the two different formulas which are mostly used by the SIW community to design any integrated waveguide. So basically the region where we want to keep our SIW is this one. And this is a graph with respect to the diameter and pitch of the via, right? S is the this pitch and D is the diameter of the via. So basically the three regions are which one? So if S, that means pitch, is less than the diameter, that means the two dias are overlapping, so this is unrealizable. So this region is unrealizable. And then if your gap between the vias are much more, then the wave will start leaking from that gap. So that is the leakage region, which we don't want, this one. If you make many more vias within a certain distance, then the substrate will break. So that is over perforated region. And of course, since it is a periodic kind of structure, so then there will be
मी आजारी आहे बोल सर्दी झाली आहे आवाज गेलाय पूर्ण.
Okay, so since this is a periodic structure, so there will be band gap type of phenomenon can also come into the picture, but we don't want electromagnetic band gap to come here. So therefore, that region also we need to avoid. So that if you choose, so these are the choice of the diameter and pitch of the SIW which we can choose if we want to make a successful SIW which will work with the TE10 mode design. Yeah, so this is just a design example with dimension just to show you that how it works, and you can see that this This is the S-parameter response. As you can see that it is working in the 8 to 12 gigahertz, which is a X band. Okay, and the insertion loss is very small, which is expected, and return loss is also pretty good, right? And this is the magnitude of electric field and surface current distribution at the top. So with the extension of the same discussion, we can also see that the conventional waveguide-based cavity can also be formed in this SIW technology if we make in the substrate 4 walls of metallic vias like this. This can be rectangular, this can be circular, elliptical, any shape, right? And they are also referring to the same similar discussion. We can actually have effective length and effective width, which are actually function of diameter, pitch, and the physical actual dimension, and therefore we can get different resonating mode of this resonator, which is formed by the cavity structure. So this SIW cavity, the first 3 modes, typically this is just an example that they are resonating in this frequency, and if you see those field distribution at these resonating modes, this is what you will see. So by that you can actually name those modes. For example, the first one you can name as 110 TE110, the second one 210, and the third one is 120. So these two are the orthogonal modes. This is exactly similar to the waveguide cavity-based application. The similar type of modes you can find, but of course, since this is a rows of metallic vias which are making your sidewall, so definitely all the waveguide cavity modes will not be able to be implemented here in the SIW cavity. That will not be possible. But certain modes definitely you can generate and you can try to utilize them for different applications. So I'm going to show you some of the applications of how these cavity modes are utilized. So the first example of SIW based circuits or antennas, I'm starting with antennas actually, is the substrate integrated cavity backed slot antenna. So we all probably have a brief idea about slot antenna, and we have the idea about that slot antenna typically radiates bidirectionally. That means in the both direction, 0 degree and 180 degree. Now, bidirectional antennas, some of the applications is not desirable. So there is one way to make it unidirectional is that you make a reflector at the backside so that the back radiation is actually reflected back to the front side. And one of the way to do that is that you make a cavity. So cavity back slot will actually give you those options. So, the conventional cavity-backed slot antenna we can try to implement in a SIW structure as well. So basically, this is just a first design which we made, where you put these 4 walls of rows of metallic vias, which will make the cavity-based structure, and then at the top you put the slot. Okay. So, and you try to excite this cavity with a microstrip feed line. So what happens is that you can see in the field distribution. So this is the magnitude of electric field and this is the surface current. So basically the idea is that similar to the conventional slot, that you put the slot in that position of the cavity where it can be disturbed with the surface current distribution of the cavity at that resonating mode. And then as the disturbance happens, we all know that the slot will be excited and it will start radiating. Okay, so here actually we are trying to radiate it in the second mode which I have shown, TE120 mode. Okay, so here it is put almost at the middle. So at the both side of the slot, the electric fields are actually 180 degree opposite phase at TE120 mode, because we know that TE120 means this side it is 1, this side it is 2. So there will be plus and this will be minus. So opposite directed electric field. So that configuration actually will give you the desired potential difference at the both side of the slot, and therefore the slot will be getting excited and then it will start radiating. And since there is a back reflector of the cavity, so therefore this will give you a unidirectional radiation pattern. But there is a catch. The catch is that the conventional cavity back slot will have the height of lambda by 4, so that the back reflection actually adds up with the front reflection, and then we get the maximum gain But that is not possible here because we are using very thin PCB, so that, as I said, that it needs to be low profile, which you can use in our we can put in our pocket. So therefore, the height cannot be lambda by 4 if you are using at the microwave frequency range where it is used. It is in this design was made in microwave in X-band. So essentially, what happened is that since the height is less, so there will be a little bit less radiation. But if you accept that, rest of the theory we could actually implement. So there is a optimization between the shift of the feed line from the center and the inset, and by this optimization actually you can get a better impedance matching. So this actually can be seen here in the Smith chart. So design curves are given. So as you can see that if you change the shift and if you change the inset, different points you can achieve in the Smith chart, and you can choose between these two combinations to get the maximum response. So this was the measured and simulated results comparison of the antenna, and as expected, so this is the fabricated antenna, and the gain also you can see the gain profile also a little bit shift is there, but otherwise it matches. And as you see that this is a unidirectional radiation pattern, not bidirectional, which is the conventional slot antenna would have been bidirectional, but this became unidirectional radiation pattern. And as you can see that with slight difference, but otherwise we could get it. So this slight difference is possible because this loose metallic vias cannot be exactly precisely done. There will be some fabrication tolerance. So this much shift may be expected in that. But yeah, if you make a careful design, then this can be much more closer, definitely. So the next design which I am going to show you is a different kind of structure or different kind of design which we proposed a long time back, and it was some different kind of antenna. So it name we gave was self-duplexing slot antenna, and this was the first of this concept which we proposed. After that, many of the research group in India started using those concepts, and they actually made very good designs from that. So this was the basic design from where it all started. So what we actually tried to do is that typically if you make a single antenna for both transmit and receive, and you are using two different bands, uplink and downlink for that, so therefore you will need a duplexing system in backside of the antenna, right? So which will actually isolate between transmitting and receiving section. Now that actually makes the complete circuit quite heavy. What if we can make an antenna which itself can bifurcate between this transmit and receive? So that's why this term came self-duplexing antenna. So this is what we made, an antenna with two ports. One port will be dedicated for the transmitting section, one port will be dedicated for the receiving section. So this is actually visible here. So whenever we are exciting the port 1, nothing is going into port 2, and vice versa. Whenever we are exciting the port 2, nothing is coming into the port 1, right? And that's how we can actually, and both the cases, this slot antenna, only one side the field is there, other side field is not there. So this difference of the potential will actually excite the slot and it will start radiating. So we will get the cavity back slot, that means unidirectional radiation pattern. Along with that, we will get that this isolation between the ports. So therefore we can use two defined ports for transmitting section and receiving section. So basically, if you are using some consumer application where say some wearable device where you actually need to make the circuit compact, you can use this type of antenna. So we also analyze this structure, that how actually this is happening, what is the basic theory behind that. And what we found out is that in this slot is actually making this cavity to work as a two different half mode cavity. So this concept of half mode cavity comes from the field distribution of the dominant TE110 mode. So basically, if you see the TE110 mode around the center, you can make a perfect edge symmetry, like that means the open this magnetic wall line. So that actually makes this a half cavity with this one as a magnetic on the PMC boundary. So this we separately analyzed. So this circuit and this one, as well as this circuit and this one, actually behaves exactly similar, that we can see from the field distribution, as well as we can see from the this response, reflection coefficient response. So that from that we actually demonstrated that it is actually behaving as a pair of two half mode cavities, even if it is a single cavity. So essentially we get our desired response, like isolation between the ports, and both gets its own resonant frequency. The gain profile also shows that once it is excited at this frequency, nothing is being radiated here, and the vice versa. And we also get the unidirectional radiation pattern at the both frequencies. So that's how the complete duplexing application we are seeing in a single antenna. So that's why we termed it as self-duplexing slot antenna, cavity back slot antenna. Oh, sorry. So yeah, we also tried to manipulate these different cavity modes. What are the applications we can use for? And finally, we succeeded to utilize these cavity modes to get higher gain of the slot antenna. For that, what we have done is that we have used a aspect ratio, this length to width ratio we changed and make it much higher. So what happened is that if you see in this type of cavity, we actually got a different type of field distribution here. And this is not the conventional cavity-based field distribution, which is sinusoidal in nature. You can actually see it here. So the conventional sinusoidal field distribution will be like this blue one. But what we got here was this red one. So how this type of unconventional field distribution you can have in a cavity? So we tried to analyze that. We did some mathematical calculation, and what we found is that a typical M0 mode will have normalized component, will have this type of expression, right? Where this is along the length and this is along the width. Now, what if, so this length to width ratio, which since we are changing, so what will happen if you see the mode chart, the different modes are coming into close frequency ranges, close resonant frequencies. That means 110, 210, 310, 410, 510, all are coming within very close range of frequencies because of this dimensional aspect. So basically what we did is that by changing the dimension, we tuned them into closer contact. So that may actually, since the field distribution of these modes are similar direction, similar electric field, so therefore there is a chance that they will start mixing with each other and make a hybrid type of mode. So therefore we can try to predict this particular condition with a replacing this sinusoidal distribution with a function, and that function will be combination of different modes. So this is for the 110 sine pi x by L. The next one is the 310. Next one is the 510, then 710 and 910. And the coefficients you can start changing and see whether can we fit this field distribution with this type of function. And what we found is that with this function, we could actually predict the field distribution. You can see that this red one, sorry, the black one is taking the first 3 terms, and the green one is taking the first 5 terms. So as you keep on increasing up to infinite series, you can actually do, and ultimately that will actually coincide with your red curve. So what is happening here is that we have been able to manipulate the conventional sinusoidal field with a different type of field distribution with this type of concept. So what is the advantage of that? How we can use that for our antenna application? So we put a very long slot there, and we tried to excite it with this field distribution. So definitely at the, as you can see in the field distribution, one side there is very high concentration of the electric field, other side there is almost 0. So the difference of the potential will actually excite the slot. So what will happen is that since we know the expression of the field distribution, now we can try to predict the excitation potential difference of the slot antenna, and that's what we did. And from that we can try to calculate the equivalent magnetic current along the slot, and from there we can predict the far field component of the electric field and magnetic field, theta and phi component at the far field. So if you, as we did that, what we saw is that instead of this higher beam width of the E plane and H plane pattern, in one plane, we are getting narrower beam width. And as we know that as we can reduce the beam width, the gain of the antenna will increase. So that's what happened. The conventional cavity slot actually gave us around 5 dBi gain. Here, we could actually achieve, I think, yeah, I have shown it here, around 8.8 or 9 dB gain, which was not possible with the conventional slot. Now, the final design, we also changed the slot with a dimension little bit. So this was typically done to ensure that there is only one resonating mode we are working, not the two modes. The conventional rectangular slot had these two modes. Here we actually made it one mode. So just to make out of band performance better, we actually little bit modified the slot antenna. And ultimately we got a very high gain with a single antenna itself. So it typically looks like this, very small design, but it gives you 8.8 dBi gain. And inundation radiation pattern, as you can see, the H plane pattern actually with lesser beam width. So it is giving you the higher gain, right? Yeah, so this is all about the cavity back slot antenna. The next one which I am going to discuss is the another application of this SIW technology, which is horn antenna. Now you all probably have seen, whoever is working in the antenna domain, they all have used this horn antenna for their measurement purpose because it is a very well-known reference antenna typically used. Typically, we use the pyramidal horn antenna. But the pyramidal horn will be a 3D structure. So that implementing in a SIW technology will be a little bit difficult. Although people have demonstrated that also. But today I will be only focusing on a sectoral horn antenna, H-plane sectoral horn antenna, which is a planar type of structure, but typically made with waveguide based technology. So here we are actually trying to make it with SIW technology so that you can make a horn antenna in a PCB, planar circuit, printed circuit board, which you can put in your pocket if required. So the design will look like this: rows of metallic vias with a flaring, just like the horn antenna. So this part is waveguide. After that, this is the flaring of the horn. And you can expect the radiation pattern looks like this. So this is the typical horn antenna radiation pattern. H-plane sectoral horn antenna radiation pattern will give us that in H-plane you will get a very narrow beam, but in the E-plane you will get a wide beam because the flaring is not there in the E-plane, right? So the only challenge is that we all know from the basic theory of the horn antenna is that the length and the flaring angle, these two are the combination of them has to be optimum to get you the certain gain, the optimum gain from this device. Now that actually makes your design very big. So what we try to do is that can we reduce that size, because ultimately we are trying to compact it. So we try to do some research in those directions, and what we found is that if we increase the one of the metallic plate after the aperture of the horn, we can actually achieve that with some little deformation. So I'll discuss that deformation, what happens. So basically what happens is that this is my aperture and then the one of the metallic plate is extended. So there will be a reflection. The one radiation which was going in the top of the antenna is now getting reflected. So the beam will be little bit tilted in the downwards, but it will actually make the beam width smaller. So ultimately my beam width smaller means that my gain will be increased. So what typically you would achieve with a longer length and flaring angle with the sectoral horn, you can actually achieve the same thing with much smaller distance, smaller size, if you can have this modification in the design. So that's what we tried to show, and we also have shown that it actually helps us to give our impedance matching much better. Working in the 28 gigahertz. So typically we try to design it in the millimeter range. So anyway, the design is small in the wavelength is in millimeter range, but still we had reduced the device to much smaller dimension, and we actually got little bit smaller beam width than the conventional one. Of course, this is not much more visible here, but the beam width, if you compare it with the conventional horn antenna, it will be smaller. And the 3D beam pattern looks like this. So it is tilted in the downside, but smaller beam width, higher gain. So conventional horn antenna, if you just make with the same length, it will be 4.9 dBi, whereas this modification actually will give you 7.2 dBi, right? And this actually we implemented in 28 gigahertz. So coming to this point, I'll also mention that, as I said, that at this point, at this millimeter wave frequency, there will be an atmospheric absorption coming into the picture. So how to mitigate that? So one of the ways is that you use very high gain antenna. So this can be one option. There can be option of array antenna, big large array. But as you are making large array, that means your size is increasing. So there are many researches going on how to actually make an efficient antenna system at those frequencies, so that the path loss due to the atmospheric absorption, and of course the path loss is also increasing. Atmospheric absorption is one. The path loss increases because the same distance here becomes multiple number of wavelengths. So there is a additional loss for that as well. So to mitigate that, you need minimum gain at least 10 to 15 dB you have to achieve. And how a compact antenna can be designed so that that much minimum gain can be achieved. Those are the research directions right now people are thinking about. So this is on those direction only. We tried that, yes, compact antenna, but still we can achieve those 10 dBi gain. The next design also, we tried different variation of the similar target, that reducing the beam width of the E plane. So H plane is anyway reduced with the help of this flaring. The E plane beam width we are trying to reduce with different combination of the technologies, so that we can achieve the same amount of gain with a smaller compact form. So what here is done is that this is actually much higher frequency. This is around 38 gigahertz we tried to design, and here we used a log periodic dipole antenna array in front of the aperture, which will actually help us to make the E plane beam width smaller. But we all see these are directors, so we will also need this. Sorry, this is not log periodic. This is the Yagi, the concept. So we will need a reflector as well. So for that, we also made a rows of vias at the top and bottom of the horn antenna to make it use as a reflector. And so what we got is that very good pattern bandwidth. That means in this range, our gain is almost constant. Our beam width is also very much constant. Although beyond that, the reflection coefficient is better than minus 10 dB, but the beam width starts changing. So we are not considering that as an operating band. And as you can see here, the H plane beam width was already smaller, but the E plane beam width also becomes much smaller. So here it E plane beam width becomes 55 degree, H plane becomes 25 degree, and we could get a very good cross-pole and copole to cross-pole ratio as well. And this is how it looks. So these are the array director, dipole director, and this is the reflector, right? And this is how the beam looks like. So conventional will give you 5.6, whereas this will give you 8.8 dBi. After the reflectors, you will get 11.5 dBi at 38 gigahertz. So those type of concept we try to use with the setup technology, and try to implement a very compact antenna with this type of small antenna system, right? So this is about the SIW technology. Now I will talk about one more technology, which for last 5 years we have started working on, which is named as substrate integrated coaxial line. I think I have almost 45 minutes, so I'll see that how much we can talk about that, right? So I'll first finish the talk, and after that I think if you have any questions we can discuss. So what is the substrate integrated coaxial line? So this is in continuation to what I discussed so far. So what I discussed so far is that implementing non-planar waveguide into a planar substrate. Here, what we are going to do is that implementing non-planar coaxial line into a planar substrate. Now, coaxial line you all are using for daily life, but they are definitely not integrated in your planar circuit board. And even if you want to use it, you need to make use of wires and all those things. Even if it is possible at the lower frequency range, at a higher frequency, if you would try to do that, they will also have these radiation issues and all those things. So basically, it is not very good idea to do that. So first question will come that why we want to do that? Why not? If we have the SIW technology, why to do that? So I'll come to that point. But first, let us see that how actually we can do that. So if I see the coaxial line, this is how it looks. This was invented in 1880, long time back, and very robust and I should say mature technology. That there will be a central conductor, there will be an outer conductor, in between there will be dielectric, and since it is automatically shielded structure, so nothing comes out. So very good technology, and even nowadays also means very widely people use this coaxial line for up to millimeter frequencies. But only thing is that it is not integrated in your circuit. Now, can we integrate that in your circuit? Yes, if you make it from the this configuration to a rectangular point of view. So rectangular coaxial line will have a rectangular outer conductor and the rectangular inner conductor. In between there will be dielectric substrate. And now if you see, this can be easily made with the planar circuit board if you make a double layer structure, right? So your substrate will have the top and bottom conductor. You only need to insert a middle conductor in between. So you make a double layer. One layer you will have the middle conductor. After that you sandwich it with the other layer. You will be able to make it. So we can implement this SiC and this coaxial line in a planar substrate if you go into this way. So this was first proposed by these three people at around 2006. The technology looks similar, that rows of metallic vias to make the sidewall of the outward conductor, and the strip will be used for the inner conductor, right? Now, is it actually behaving as a coaxial line? So to show that, this is just to, these arrows are just to show you that yes, this refers to this inner conductor, and this outer conductor refers to the top and bottom conductor as well as the sidewalls, right? So whether is it working as a coaxial line? First of all, the response. If you see the response from DC to 50 gigahertz, it is working pretty good, right? Even after that also it may work pretty good, right? So this is one of the difference with the waveguide. Waveguide single mode operation will only work for a certain frequency range. This coaxial line will work from DC to for very large wide band. So if you want to use your system to work in different frequency bands, for SIW you have to make different circuit. For Sicl, this one you can use the same circuit, same technology for different applications. That is possible. So that is one of the advantage of the Sicl technology over the SIW technology. But of course, the fabrication complexity becomes higher because you need to use double layer. So this is just a comparison of the field distribution of the two structures. So this is the conventional coaxial line, and this is the Sicl. So as you can see, with some deformation, but still you have those radially outward lines here as well. So it is actually behaving with as such of a coaxial nature. And we have also tried to figure out the propagation constant, and we found that yes, it is actually TEM based line, integrated in a planar circuit board, but still it is behaving as a TEM based line as well. So why Sicl? As I said, wideband unimode single mode operation. Then this is a non-dispersive compared to SIW, which is dispersive in nature, shielded. So at millimeter frequency, definitely it can be used. It is planar structure, so very easily integrated into the PCB board. Better Q factor, ease of fabrication compared to coaxial line. If you want to make a coaxial line, you need certain instruments to do that. But if you can do this, the conventional PCB technology can do that very easily. So that's one of the advantage compared to the conventional coaxial line. So to demonstrate the idea, we first tried with a transition which can be made easily. So we tried to make a transition from Microstrip to Sicl. And this was our design, and so which we did. So basically, we made a Y-shaped slot type of thing with the Sicl microstrip line, and this was measured. I'll show you the measured response. But first, let me tell you that how this transition works. So basically, we all know that microstrip line is actually quasi-TEM line, which looks like this, whereas the SICL, as I said, is a complete TEM based line, which is the field distribution looks like this. So basically, we need to make from here to here. So how we did, we gradually this gap of the slot is actually gradually changed. Slowly, it is converging into a point. So in these reference points I have shown here. So A dash is the point here where the quasi-TEM is there. Then B dash is the starting of the upper layer with a gap. So in the gap, the field distribution looks like this. Then as the fields are, this gaps is converging, in CC as you see that this field distribution from the quasi-TEM, it is gradually coming to the radially outward type of configuration. And ultimately when it converges, we could make from here to here. So at the this D dash where it is here in the Sicl, it is actually becomes. So gradually from quasi-TEM, we are trying to make it. So since this is a slot slave of structure, so there will be a field distribution from this side to this side. So that's what we are seeing here. Now, once it is trying to converge, this field distribution, this lateral direction field distribution, which is we are exciting by mechanically, I mean forcefully, those will actually help us to get this radially outward type of field distribution, which we are seeing here. So ultimately, we could get this radially outward direction. Both are quasi-TEM to TEM, so transition is effective, but only this field conversion, mode conversion was required that we could achieve with this simple type of structure, right? And so we fabricated it and measured it. So this is the typical configuration which we did. As you can see, very small line if you try to measure, because it is in millimeter wave, we try to do it. So we actually measured it from DC to 40 gigahertz, and as you can see, it works perfectly right from DC to 40 gigahertz, which was predicted. And this is the phase response and group delay response. So the non-dispersive nature also we could show with the measured results. So this was the first example of the Sicl line which we made. And after that, we tried to design different circuits. So I'll try to discuss some of them here. The first one I am discussing is a dual band balloon. Now, as I have stated already, that 5G applications is actually trying to be implemented in different bands. One is sub-6 gigahertz band, one is millimeter wave band. Now, a single technology which can be worked into these two bands is very challenging to do. So typically people what are trying right now is that only focusing on the sub-6 gigahertz, they are trying to make it in microstrip. But if they want to switch it in the millimeter wave, they are actually making different circuits for that. What we are saying is that you can use this SICL technology, make the both circuits with the same technology, so your circuit will be much more easier to design. And with that target, we actually tried to see, can we make a single circuit which can work in these both bands? So we tried to make a balloon which can work in the sub-6 as well as the 28 gigahertz, and that we made it. So basically here, what we did is that this conventional lambda by 4 section of the branch line coupler, we replaced it with the T section. So this is a very, you can actually try to get this expression. So basically this is a cascaded line section. So you can have a ABCD matrix and try to implement that, and trying to equate this with the conventional ABCD matrix of the conventional lambda by 4 line. So this is the ultimate cascaded section ABCD matrix, that if you can equate with the conventional ABCD matrix lambda by 4 transmission line, what you will see is that, so this is the conventional one. If you equate that and try, you will get 4 equation and you can solve it. So ultimately you will get this type of expression. So P and Q are the two integers which you can choose, and RV is the frequency ratio, and you can have a design graph like this. So basically this tells us that you can choose your P and Q according to your wish to achieve different value of this Z1, Z2 and theta 1, theta 2. What is this theta 1, theta 2, Z1, Z2? This section. So Z1 is this one, this line, theta 1 is the length of this line, the same is here, and Z2 is this line and theta 2 is this line. So what should be the value of that? that depends on what are the two frequencies where you want them to operate. And these are the equation for that, the design equation. And you can put your values here and try to find out what is realizable. Of course, this y-axis is actually the impedance graph. So definitely there is a fabricational challenge. You cannot actually make very high impedance, characteristic impedance with this conventional PCB technology because there is the dimensional limitations there. So therefore you have to actually choose your P and Q very precisely so that it is in the realizable range. So with that you can actually get a final design. And we did that. We implemented the design and we saw that it is working in the 5.5 and 28 gigahertz, sorry, 26 gigahertz. Both are two different bands of the 5G. And in between two bands, there was the isolation was also very high. And therefore, we could get very, which one we were expecting that we got, the two different bands. It was working as a and the amplitude phase imbalance also is that this is also pretty good at those two bands, right? So this is just one application. The other application which we did was the crossover. So wideband crossover we tried to implement with expand from DC to 20 gigahertz. And so far, people have implemented it with, but not that much wide bandwidth. At DC to 20 gigahertz, a single crossover circuit will be used that people couldn't demonstrate, but we could demonstrate it with the Sicl technology. The advantage of the Sicl actually utilized here that it can work for a very wide bandwidth. And since it is a pure TEM based line rather than the quasi TEM, so the phase difference, phase delay between the two lines also became very, very small, which is one of the advantage of this crossover, which people couldn't implement with so far technology. So basically it looks like this. The layer wise, if you try to bifurcate, this is like this. So this is a dual layer system, right? So at the cross, actually, you have this small section of DCPW in the two lines, right? And so this is just an analysis point of view that with different. So these are the range of the realizable dimensions which you can use, and accordingly you can see that what are the characteristic impedances we can be able to realize with this Sicl technology. And accordingly, you can see that which of the height of the substrate you can use so that your insertion loss becomes smaller. So one of the challenge here, if you see here, that here we are terminating here at the port 2, but ultimately, if you want to excite it, you need a transition. Now, the challenge in the transition is that if you use different height of the substrate, your insertion loss increases. So there is a optimum dimension you have to choose. You cannot choose any dimension for that. So those things with study, actually, you will get an idea, and that's what we reported all our studies in these papers. And also there is a these dimensional complexities there is that if you see here, these are the two overlapping GCPW line. So what we saw is that with the height, actually there is a, if you increase the height, the isolation increases, but the insertion loss decreases. So there is those optimization also is required. What should be the actual point where you can keep your design? So all this we have studied quite widely, and then we reported it. So as you can see from the field distribution, whenever we are exciting this line, nothing is going in the other line, and the vice versa. So the crossover is working fine, and this was the fabricated result. So this was in the microwave range. From DC to 20 gigahertz it worked, and this is the insertion and isolation. So you can see the measured results are quite in comparison to the simulated result one, right? And this is the one, the group delay one, also very low since it is a TEM based line. And as you can see, the phase difference or path difference between the two lines are pretty small, which people couldn't achieve with our technology. So we demonstrated that the Sicl is very, very robust in those types of application, right? Yeah, we also tried to implement SICL filter. So this filter was in KU band, that means 18 gigahertz. higher than the conventional band which we are using right now. So the dimensional complexity remains here. And one of the effective thing here is that we could demonstrate here is that if you deform the outer conductor, keeping the middle conductor constant, you can actually achieve those filter response, which actually proved that, yeah, the radial line from center to outer conductor exists, which we could utilize for this filter application. So this is the dominant modes, the first higher order mode and the next higher order modes. And since it is a TEM based line, which we could show here is that there is a very good out of band performance we could predict, because this is the first two higher order modes and next two higher order modes which are orthogonal to each other. Since they are two orthogonal, so we can actually utilize them to get this perturbation of the mode and get a transmission zero. So that is there, and also this out of band performance we will be able to achieve because in between there is no modes. And this is the range of the characteristic impedance which we could get if you deform the outer conductor. That also studied and reported. So this is the fabricated filter, which is pretty small if you see here, and this is the measured result, which agrees well with the simulated response. As you can see, the out of band performance in the both side of the band we could achieve. This is because of the Sicl technology, the pure TM based technology, we could get that. Right. So all these details are given here. These are some of the examples of the circuits. Now I am going towards the Sicl based antenna. So we tried different combination of the Sicl based antenna. How much time I have? Hello?
Yes, sir. Yeah.
How much?
25 minutes or 30 minutes maybe.
Okay. Okay. So this first design which I am discussing here is we tried similar to the SIW cavity back slot. We tried to see can we have SICL based cavity and try to excite them. So one question may come that if we can do that with the SIW, why to go for the SICL? So one of the advantage of the SICL is that since it is a TM based technology, so the guided wavelength here will be much smaller than the T110 based SIW based cavity. So the size of the cavity becomes smaller. So ultimately your design becomes much smaller at the same frequency. So we tried to implement that in the 28 gigahertz, and this was the first cavity backed slot antenna which we reported with the help of the Sicl technology. So you can see the dimension with respect to the lambda naught, which is much smaller than the SIW based technology. So one of the challenge was that what are the modes which are occurring in this particular Sicl based cavity. So we actually first did mode analysis, that what are the different modes occurring. So we saw that the first mode was TM based mode. So basically here the middle conductor is this one, which is short circuited at the both end. Okay, so the middle conductor, both two of the sides are having this PMC boundary, and two of the direction we are having PEC boundary. So this is different from the SIW based structure. Little bit difference is there. So accordingly, the modes will be also different. So what we saw is that the first one was the TEM based mode. The next two mode are occurring along this BB dash axis, which is here. So one axis is A dash and one axis is BB dash. So the next two modes are occurring in BB dash axis, and they are two events and not events in the degenerate modes, which are occurring almost at the same frequency, but one is even mode and one is odd mode. So one is sinusoidal in nature, one is co-sinusoidal in nature, and both are occurring along the axis. The next mode, the fourth mode, is actually higher order mode of this one. So here it was one variation, now it has two variation. So that's how this type of variation, all these variation, if you see, they are TEM based nature, and they are very different from the SIW cavity based modes. So and one of the major challenge was, can we utilize these modes to excite a slot antenna? And therefore, first we studied that and we made a mode chart, and these are the different mode charts. So as we said that these two modes almost working in the same frequency range if you don't have any perturbation. Now, what we did is that we tried to make perturbation with the help of the slot antenna at the top plate. What I saw is that we could actually get difference of the field in the both sides of the slot. So now, as we know that the difference of the field will create potential difference, which will ultimately excite the slot, and the slot will start radiating. And the back reflection is there because of cavity, so we will get a unidirectional radiation pattern. So this is the first design we tried at 20 gigahertz antenna, cavity back slot. It was very small antenna, and we could measure, we could report the measured result at 28 gigahertz, and the radiation pattern also you can see here. So it was unidirectional radiation pattern. The slot was cut in the bottom plate, so that's why it is in the back side. If you cut it in the top plate, of course, it will be in the broadside direction, right? So this was the first example of the millimeter wave slot antenna made using Sicl technology. We did some more variations and reported. For example, we tried dual band response with this type of configuration. So what we did is a two slot configuration we tried to see, and of course one of them will give the dominant mode excitation, and the other one will be actually the slot is radiating and the cavity is not excited in a particular resonant mode but acting as a back reflector, and that's how this two dual nature you will achieve. And of course the dimensions of this slot you have to optimize because they are very close to each other, so they are actually very much coupled. Therefore the surface current distribution will be very much different from the conventional lambda by 2 slot antenna. So therefore there is a need for optimization for that, and ultimately we could achieve this dual band response. Both of them are in millimeter wave, and both of them are actually different bands of the 5G, where you could achieve this unidirectional radiation pattern with good this frequency response. So this also we reported very recently. We tried these two were the design which we tried with Sicl based cavity, whereas we used the Sicl as a feeding line and tried to excite millimeter wave dipoles and tried to see that what would be the response for that. So for that we first tried with in this quasi-Yagi antenna. So Yagi-Uda antenna you all know, and if in the printed form of the Yagi-Uda antenna is the quasi-Yagi antenna, where there will be the main dipole antenna, there will be a director, only one director, and a reflector. So here we tried to excite the main dipole antenna with the Sicl technology. So this is the Sicl line. Okay, so here we used initially a different type of transition, but later we found that the transition which I have shown earlier was much more efficient. So we repeat those transition later. So here this is the Sicl line. Now the one of the advantage of the Sicl line is that it already has the middle conductor, and the central conductor and outer conductor is completely out of phase. So typically a dipole antenna requires a balloon because this 180 degree out of phase between the two arms are required. But here in Sicl, it is automatically there, so you don't need a balloon. So therefore, in a printed circuit form, this is much more advantageous that you connect one arm of the dipole with the central conductor, other arm you directly connect with the outer conductor. So this is just similar concept which you typically use in a dipole antenna. You use a coaxial line. Central conductor you connect with one arm, and outer shielding conductor you connect with the other arm. That's what we are doing, but in a planar form. So it is very compact in nature, and that could excite the dipole antenna. And ultimately, we used a director to improve the gain, and the reflector part itself is being done by the Sicl. So this top conductor end and bottom conductor end, both of them are actually working as a reflector for this dipole antenna. So it is very compact. You don't need an additional thing to do here. Right. So this is the gain typically with the resonant frequency. You can see that it is almost around 7 dB gain we could achieve, and there was this. This is just a study to show the variation. So then this dipole to the top conductor distance, if you vary how the gain is varying. Of course, the reflector to main dipole distance, if you vary, that is from the Yagi antenna, we know that the gain will vary. Accordingly, if you vary this length of the director, of course, these optimizations are there. This is much similar to the Yagi concept. That's what we saw. And also there is this variation of the front to back ratio and the gain. So what you can see is that if you just vary the dimension, this director to dipole distance, probably you will be able to achieve higher gain, but with the expense of the front to back ratio is degrading. So actually you have to see a optimum point where you can put your director so that the better front to back ratio you could achieve, and as well as the gain. So this is the final design, which is quite wideband, covering 26 and 28 gigahertz of the 5G band, and with a pretty good gain around 8 dB with this profile, almost constant throughout the band. And this is how the response looks like, E-plane and H-plane pattern. So that we could achieve that SICL-based feeding network we can use to excite the dipole antenna at millimeter of frequency. We also just, try to do different combinations to get broadband and wideband applications. So here we tried with the multiple of combination of dipoles, and what we saw is that different lengths you can combine. So basically they are using as a multiple resonator we are trying to excite with the SICL technology. And this is a concept of staggered tuning, you can say, where two resonators are there, they are coupled to each other, and together they will give a wide bandwidth. And that's what we could see, that you can tune the lengths of these individual arms to tune the bandwidth of the response, ultimate response of the antenna. So and this actually also achieved in improving the gain. So with the single dipole you could achieve around 7 dB. With the two dipole combination you can improve the gain a little bit, you will be achieving 8 dBi along with the bandwidth. That's what we could achieve, and you can see that the beam width is much smaller, which is actually helping us to achieve the higher gain of the antenna. We tried these broadband. We know that conventionally the bow tie slot antenna, bow tie antennas are typically gives broadband response. So we tried that one also, and as expected with the SICL feeding also, it also gave a broadband response. So the feeding is very simple. At millimeter wave, if we are using microstrip based combination, then there is a chance of this radiation loss as well as surface wave. But SICL will help us in those currents, and that's why you use the SICL based feeding. And you, in addition, you got this replacement of balloon. You got the additional back reflector. So all this helped to improve the gain and as well as excite the slot antenna. So this is the field distribution of the dipole antenna. You can see here, this is the surface current distribution. The oppositely directed current you can see here, and we could achieve around 9 dB gain in this with the broad bandwidth because of the SICL. Because if you use microstrip, your back reflector is not there and the balloon is not there. So those are the advantages which you can achieve with the SICL based feeding in the millimeter wave frequency. We very recently started working on the this switchable polarization of the this dipole antenna configuration. So this is the one we first tried, that two dipole we tried to combine with the SICL feeding. So basically this middle arm is actually common. So this arm and this arm is actually one dipole, and this arm and this arm, this common arm is making another dipole. And since they are orthogonal to each other, so one of them will be radiating in the plus 45 degree and one of them radiating in the minus 45 degree. And in between we can use a diode, switching diode. So switching on and off will actually change the direction of this antenna. So this is what we tried to design with the SICL feeding network at millimeter wave. And what we found is that yes, if we make diode 1 on and diode 2 off, this is the field distribution. So the plus 45 we could get the radiation pattern, and the vice versa for the other diode on, this one is off. And we also saw that the response in the both cases exactly same, as well as the this radiation pattern is similar. So here you can see that what is copole here for the first case is cross pole in the second case. So one is at the plus 45 in the E plane and one is at the minus 45 in the E plane. So we could switch the polarization in this type of configuration. We also tried to extend this concept because here the gain was not that much higher. So we wanted them to be in the array configuration. So for that we used separate these two things. So we can use the switch in the excitation port now. So they are side by side each other. So this is the unit element concept only. And then the same similar way that once we are exciting the port 1, port 2 is not being excited and it is radiating in the plus 45 degree direction. And whenever we are exciting the port 2, it is radiating in the minus 45 degree direction, whereas this one is not excited. But since here these are side by side and in between there is nothing, so isolation is a little bit less. So what you can see is that some part of the fields are there. So that is one of the disadvantage of this particular design. So the reflection coefficient response is exactly similar, and this is the response. So as you can see, the gain is much lower, 3.36 dpi. So what we did is that we made a array of 1x4 for both the antenna, and with the help of the plastic screw. And then this is the final response, where once you are exciting the one side of the array, it is radiating in the plus 45. Once you are exciting in the other side of the array, it is radiating in the minus 45. But as I said, since the isolation is a little bit less, so some small radiation you will be seeing here. But the array actually improves the beam width, so therefore you will be able to achieve much higher gain in this case. So here the gain response is 7.6 dBi you could achieve. So switchable polarization with 7.6 dBi at 26 gigahertz we could achieve with this combination. So this is just a comparison of that. So I'm moving ahead. So we not only tried with multi-layer array, we also tried with only simple double layer configuration of the Sicl technology. So to get a single Sicl platform to get the array application as well. So for that, what we did a series fed combination. So this is basically, this is what is the unit cells you can see. So this is a short circuited line. You see the middle layer is actually short circuited. So once it is short circuited, this is a standing wave will form. And if you put a slot at the lambda g by 4 from this short circuit, that will actually disturb the surface current much more. And therefore you may get a radiation from this. But one of the challenge was that the width of the Sicl was very small. So we had to use different combination of the slot structure. So we used a C type of slot here. And that actually we could achieve to excite the antenna, the surface current distribution, and ultimately we got a radiation. So this one is lambda g by 4 from the short circuit, and from here to here it is lambda g by 2. So the field distribution will be actually opposite to each other. So therefore the orientation of the slot we changed so that both of them are radiating with the same phase, so that they don't cancel. They get interfered constructively and get a good gain. So this is the combination we used, and ultimately we made 2x4 array antenna configuration. So this is the response of the power divider which we gave, and so yeah, so this is the response. So this is the first 1x2 slot antenna response, which is the unit element, and this is the 2x4, the complete array response. So both of them are pretty close to each other, and this is how you can see the power is dividing in between the two, in between all the elements, and they are excited all at the same time. So the phase is same, and what we could achieve is that very pretty good beam width in the both E plane and H plane. And of course, since this is an equal excitation, so there will be a side lobe that we cannot right now at this point we could not do anything. But yeah, we are actually looking after it, how to reduce those things. So that we did on in the planar form. You can say the high gain array antenna at millimeter wave using Sicl technology. And this we tried to do. And you can see the cross polar component is also pretty small. Yeah. So we extended the design with a 6x4 slot array combination, and that also we reported. So basically, the equivalent circuit will look like this. So this is what I was saying, that this will be short circuit. After that, the first slot, then the second slot, third slot, fourth slot, which will have their own equivalent impedance. So basically, the design will rely on that all these should sum up with the characteristic impedance of the line. So you can choose those dimensions such that this happens, and therefore you will get an impedance matching, and all of them will be getting equal amount of excitation, and they will radiate simultaneously. So that equal excitation will be also helpful. That has to be achieved. So therefore, that slight change in the slot dimension also required, so that the disturbance of the surface current can be varied. But yes, here is definitely a challenge is there, because the current distribution mostly concentrated here. So the placement of the slot is very crucial to get those equal excitation. So what we additionally did here is that in the first design, we only put the slot in the top plate. So the radiation was only happening in the broadside direction. Here we simultaneously put the slot in the top and bottom. And as we know that the top conductor and the bottom conductor are actually connected, so that both of them are actually constructing the outer conductor. So they are in the same phase, right? So the field distribution will also be similar. Only thing is that the direction will be just surface current distribution will look like also in the same phase. So what is happening at the top, we can also use at the bottom as well. We can put a slot there, and we can try to excite the slot with the disturbance of the surface current. The only problem will be happening because the total power is same. So basically it has to be divided between the two slots. And this equivalent circuit now becomes a little bit more complicated, because here we have two slot impedances which are in parallel. So but ultimately you can try to adjust the dimensions such that this actually automatically. So the two parallel equivalent, if you put as a 0, 1 by 2, the circuit becomes similar, and then you can try to achieve the desired characteristic impedance, the summation of them as a equal to the characteristic impedance. So we tried to do that, we achieved that. So this is what we achieved so far. Different, and this is just 6x1, and then we also did 6x4. Both of them are rotating in the same frequency range. And the advantage is that now we could achieve high gain dual beam radiation pattern, right? So in the both direction it is radiating, but the beam width in the both cases are very, very narrow because of the array antenna combination. So that we could achieve with this type of configuration. Right? So with that, I come to the end of the today's talk. So basically, I tried to give you a glimpse of the ideas of different technologies which can be useful for millimeter wave application for typically the consumer application, but not limited to that. We can also do the application extend to defense as well as space as well. Of course, there are challenges to do that, but I believe that that is also possible. And yeah, we tried to demonstrate some of the millimeter wave applications as well with some fabrication and measured result. We will continue doing that, and hopefully in near future these all can be used by industries as well, and try to get more use of the millimeter wave for people's use. So these are my research group. I am thankful to them. Because of them, actually, I could report all these papers, and today I could discuss all these results with you all. So this is my contact information. If you all want to contact, you can directly come and contact me at any time. So thank you all for listening to me.
Thank you, sir. Now we have 15 minutes to clarify the doubts if there are any. So anyone, please feel free to ask if there is any question.
Hello, sir.
Hello.
Sir, I want to understand what do you mean by substrate integrated in waveguide or in coaxial line?
So the conventional waveguide is, if you have seen, it is a kind of something like that. If you can see that, this is very small. Of course, it will be very big. So pipe kind of structure, which is not a PCB. But what I have shown here is you can actually make it as a single PCB. Right. So basically, we're trying to integrate waveguide circuits into a planar circuit board or printed circuit board. That's why we are saying substrate integrated. Substrate is dielectric substrate, which is used for the PCB. And we are trying to integrate the conventional waveguide and conventional coaxial line into PCB. That's why we are calling it substrate integrated waveguide or substrate integrated coaxial line. In general, it is substrate integrated circuits.
Okay, sir.
Any more question?
So, if from participant side have you any query, please feel free ask.
Hello, sir. Sir, in one slide you have shown the design rules, S by D like that. So how these design rules are coming?
So I have shown in one of the slides that how they studied with variation of the dimensions, how the cutoff frequency is varying. So from there, you can actually get a closed form expression from these design graphs. And from that, actually, they came up with the design rule. Of course, that will work only within a range of the dimensions. But typically, we work on those dimensions, so it works fine in those ranges.
Okay, sir.
Good afternoon, sir. Hello?
Yes, I can hear you.
Yes, sir. So I have a question regarding the basic of that millimeter wave antennas. In the millimeter wave antennas, we have a limitation regarding the transmission distance. The wavelength is very much small, and if we are going to deploy these millimeter wave antennas for the different civilian application, so the repeater and booster is required in everywhere. So under this conditions, it will be possible to deploy these millimeter wave antennas under the for the civilian application nowadays, because the industries are putting that's why that is the basic question.
So the thing is that as I said, the 5G has different frequencies to talk about, and not all of them will be used in everywhere. For example, if you talk about metropolitan cities where dense population is there and everyone is trying to use that much amount of bandwidth, they are probably you need those millimeter wave frequency ranges. So you can expect that cities like Delhi, Kolkata, all the metropolitan cities, you will have dense base station grids. Means everywhere and here and there you will have these repeaters and antennas, all those things. But as the population will be decreasing, if you go outskirt, there you probably will not require it. So then you have to go to other strategy. So what I'm trying to say is that 5G is not very much specific to a particular technology or particular band. They are trying to expand and cover all the frequency ranges, all the type of possibilities, and depending on the situation, they are going to use all. The ultimate target, what I said, the three pillars, this enhanced mobile broadband, ultra reliable low latency, and machine to machine. How to achieve that for different scenario will be different, solution will be different. Of course, this makes a challenge for the service provider. So maybe that's an issue to research and how to get a single solution. In fact, that's why I said that this would be one solution, that if you use one technology, you can achieve both the things probably. So you can get that way.
Okay. Okay. Thank you. So there will be a different frequency ranges for indoor and outdoor application actually, no, sir? Under
Yes,
5G.
there has to be. There has to be.
Okay. Thank you. Thank you.
Any more question?
Kindly share the PPT so that in future we can prep for this. Hello, sir.
Yeah, I'll contact. So some of most of them are this published. So I'll see what I can do. I'll contact the organizer and do that.
Okay, sir. Thank you, sir.
Okay, if possible, so expert will I will communicate with experts. So if possible, so then I will share with all the participants.
Yes, sir. Many useful things are there. That's why.
But I think you have recorded the video, so anyway, that is available.
Yes, sir. Yes, sir. It will available in YouTube also, sir.
So
No issue. Video recording also available.
You all will get that.
Yes. So I think that is no more question from participant side. So thank you, sir, for sharing your research experience, and I would like to thanks on behalf of our institute, NIT Manipur, from the Department of Electronics and Communication Engineering, for your valuable talk. And I expect in near future also we can expect your participation at your for your valuable
Thank you for inviting me. And of course, I'll try. I'll love to come to the campus.
Yes, sir.
Your institute.
Okay, sir. Thank you.
Okay.
Thank you very much.
Okay. Thank you. Thank you.
Okay, sir. Okay. Thank you.
Thank you, sir.
For the second sessions, it is attendance is available on chat box. Please fill it. And our next session, that is the third session for day 1. It will start 3:30. Right now 3:20. So sharp 3:30 we will start our next session. So please stay with us. So just 5 to 6 minutes breaks. After that we will start our third session.
Hello.
Yes. Hello.
Sir, am I audible?
Yes.
Sir, my voice is audible to you?
Yes, audible. Please ask.
Okay. Sir, is there any WhatsApp group for this FDP, sir?
Yes, WhatsApp group is there.
Okay. Sir, actually, the mobile number I registered on ATAL portal website, the WhatsApp service is not accessible. So, if possible, sir, send me the WhatsApp group link so that I may join the link.
Actually, when I was
I will add him. I'm sharing my number. I will add him.
Someone is talking right now, I think. Okay, let me finish. When I was share the all details regarding the FDP program, that time also I mentioned that there is also a WhatsApp group. So for the first communication, we are using this WhatsApp group.
विदाउट ग्राफिक्स के पिक्चर देखने होंगी
So if you share your WhatsApp number through this over this mobile email ID, then we can attach your number or add your number. No problem.
Okay, sir. Thank you so much, sir. And sir, session 1 attendance I didn't mark. I forget to mark that attendance. Actually, in the beginning.
Okay, no issue. If you forget to give the attendance, so it is automatically recorded by our software. Okay.
Okay, sir. Okay. Then no issue.
So for the safety purpose, we are using this Google form also, and after that we will verify it with our software attendance.
Okay, sir. Okay. Done, sir. Thank you, sir.
Okay.
सपोर्ट तू काहे भैया ऐसे पगार की तरह कर रहा है? मार्कशीट पाठवू का सर? मी कॉल करतो तुम्हाला, म्हणजे 12 ते 13 नाही म्हणणार. 12 देखो सर, अपने को लग रहा था भाई ये भी एकदम फ्रेशर है, लेकिन वो एकदम एक्सपर्ट लेवल पे निकल गया. ऐसा रहता है सभी का. ते फॉर्म नव्हते का त्याची, बायोडाटा वगैरे घेतला होता आपण आयकेसीचा, त्याच्यात त्याचा फोटो नव्हता विशालचा. म्हटलं पासपोर्ट फोटो भेज, त्यानं हा पाठवला. ये भेजा चलता क्या बोला, मेरे को क्या लगा क्या बोला फोटो बायोडाटा.
चेतन जी अपना माइक अनम्यूट कर लीजिए.
Sorry for the interruption. Chetan sir, you have been annoying the entire session. Please don't do that. We are eager and we are here to listen to that.
परिहार. डिपार्टमेंट रिपेअर चांगलं सुरू आहे का वायफाय? बॉलिवूड वाल्यांनी काय केलं, त्याचा हिंदी डब व्हर्जन जो आहे तो सध्या रिलीज न करण्यासाठी त्यांना पैसे देऊन
बस एक बाकी है.
Hello.
Hello, am I audible?
Yes.
Okay, sir. Okay, now we have Dr. Rakesh Sinha, who will take us through the importance of phase shift in the design of impedance matching network. Dr. Rakesh Sinha received the BTech degree in Electronics and Communication Engineering from Kalyani Government Engineering College, Kalyani, in 2008, and the MTech and the PhD degree in RF and Microwave Engineering from the Indian Institute of Technology, Kharagpur, in 2011 and 2016 respectively. From 2008 to 2009, he was the Department of Robotics and Automation, Central Mechanical Engineering Research Institute, Durgapur, India, as a Junior Research Fellow. He was an assistant professor with the Department of Electronics and Communication Engineering, GIS College of Engineering, Kalyani, India, from 2016 to 2017. During 2017-18, he was associated with Ulsan National Institute of Science and Technology, South Korea, as a postdoctoral researcher. He was associated with Jungnam National University, Daejeon, South Korea during 2018-19. Currently, Dr. Sinha is working as an assistant professor at the Department of Electrical Engineering, NIT Rourkela, India. His current research interests are in the area of multi-port network synthesis, impedance matching, coupling and decoupling networks, phased array, and computational electromagnetic. Dr. Sinha has introduced many novel concepts like the transmission phase of the matching network and multi-port network, and their importance, port decomposition technique, and its application, etc. He also co-invented the theory of couple characteristics mode. Thank you, sir. Over to you, sir.
Good afternoon, everyone.
Good afternoon,
Am I
sir.
audible to you?
Yes, sir.
Yes, sir. Audible, sir. Yeah, audible.
Okay. Okay, so today I will discuss one of the very important topic, that is basically impedance matching network. So without impedance matching network, you cannot do, means basically you cannot design any component or any antenna also, okay, without impedance matching. So impedance matching is one of the basic and fundamental concept every RF engineer should have. Okay, so otherwise you basically design something wrong, and basically something that which is not basically not basically how can I say? So basically it is not working. Okay, so without impedance matching. So impedance matching is a very important concept. Okay. Now, as the title says, that it is importance of phase shift in the design of matching network. So some of you are already familiar with how to design impedance matching network, but you are not familiar with that how that phase shift come into the picture in the design of impedance matching network. Okay. So let's start our discussion. So before going into our main discussion and what are the flow of the discussion, I would like to read one quote from Professor Albert Einstein, that is, to raise new question, new possibility, to regard old problems from a new angle requires creative imagination and marks real advance in science. So basically impedance matching network is a very old topic. Okay, so when that RF technologies come, that in that time of itself, that impedance matching network concept was there. Okay, and I was already familiar with impedance matching network. Even when I was in MTech, so that time I studied about impedance matching network and how to design impedance matching network using Smith chart. Those things we have already studied. But one of the very important thing that has not been addressed before 2016, when I published my paper, that matching network into viewpoint of transmission phase shift. That is basically the phase shift of matching network. So when we basically design matching network, we do not consider the phase shift. But there is a reason behind that why we don't consider and why we don't bother previously. But in the upcoming days or in modern day technology, you need to understand the phase shift concept of impedance matching network. So otherwise, it may lead to some erroneous design. So I'll show you some example that some very big people may have done this kind of mistake without considering transmission phase shift of matching network. Okay, so the flow of this presentation will be something like this. So at first I'll discuss introduction and then network parameter of matching network. So what is the network parameter of matching network? And then some simple matching network design. So for example, L match or pi match or T match network design using the concept of transmission phase shift. And then I'll try to discuss about some of the symmetric matching networks. So what is symmetric matching network and what is asymmetric matching network? So in general, the matching networks are asymmetric in nature, but there are special cases that in that case, it may basically electrically symmetric. So when I'm talking about symmetry, it's basically electrically symmetric. Okay. And then I'll show you some of the experimental verification of the proposed concept and then conclusion. Okay, so first introduction. So what is impedance matching network? So impedance matching network is one of the fundamental and crucial components spanning over the entire spectrum of RF and microwave and millimeter wave. In general, it is passive, reciprocal, lossless, two-port network. So please note that it is not a one-port network. It is a two-port network. Okay, so because we basically design, okay, till now whatever we design, so basically based on one-port concept, not two-port concept. So I'll show you how to design that one-port concept. Okay, and then I'll show you how to design based on the two-port concept. Now, the main application area of impedance matching network are basically antenna feed network design. So if you have designed a badly designed antenna, but it is radiating properly, but not match. So in that case, you can connect a matching network and you can match it in the design frequency. Or you need to match an amplifier. Okay, so you can design the input matching network and output matching network of an amplifier. Okay, or in the design of power divider or combiner, RFID, impedance compensation network for energy harvesting, wireless power transfer. So these are there are various lots of bigger span of application of impedance matching network. Now, what is impedance matching network? So it is basically designed for maximum power transfer. Okay, when delivering AC power, maximum real power is delivered to the complex load when the load impedance as seen through an impedance matching network by the complex source is equals to the complex conjugate of the source impedance. So what does it mean by that? So let me. Okay, so what does it mean by that? So basically, let's say you have a source. Source means basically voltage source. Okay. And obviously the practical voltage source having some impedance, internal impedance. Okay. So let's say this is ZS. Okay. Now, you need to connect, let's say the source is basically, you can consider it is an amplifier. Okay. So it is the output of an amplifier, can be equivalently modeled as a Thevenin source. So it is a Thevenin source. And you need to connect a practical load. The load may be a speaker or maybe antenna or anything. Okay, so you need to connect a load. So for maximum power transfer, you need to connect the load should be complex conjugate. The ZL should be complex conjugate of ZS. Okay, so for maximum power transfer. Now, if it is not true, okay, so the load, you cannot control the load. So we cannot control. So load is already defined and the source impedance is also already defined. Okay. So for that, you need to connect a matching network in between. So you need to connect a matching network. Okay, so it is your ZS source impedance and connect the matching network. Okay, so it is a basically reactive network. So consists of LC or basically ideal transmission line. And now connect the load here. Okay, now here after connecting this, So this network, the main property of this network is basically this convert this ZL into conjugate of ZS. So this is the main purpose of this network, the impedance matching network. Okay. So this is a viewpoint. Okay, so I have represented them as a black box. Okay, so black box, this model can be modeled as a 2-port parameter. So for example, you can model it by ABCD parameter. So for a lossless network, A and D are real and B and C are pure imaginary. Okay, so B and C part of a lossless network are purely imaginary and A and D are purely real. So that's why it has been written like this. And what is do? So it's basically convert the ZL into conjugate of ZS. So if you look into this, so it is basically look like a conjugate of ZS. Or in the other way, we can say the same network is basically if I connect the source at the port 1 and in the port 2, if I look into the network, then what I look, it will look as basically conjugate of the load impedance. So it can be proven. Okay, so it's not a difficult thing to do. Okay. Okay, so what are the type of network? Okay, matching network. So there are mainly 3 type of matching network are possible. One is basically lumped. So it's basically consists of lumped inductor capacitor, or maybe using transmission line or basically coupled line. So those kind of techniques, basically distributed line. Okay, so distributed technology or combination of lumped and distributed. So this is sometimes called mixed topology. Okay, combination of lumped and distributed element. Now, in the lumped element topology, there are 3, you can say, basic topology are available. One is L match network, pi match network, and T match network. So the name has been provided based on the shape of the network. Okay, so this name have been provided based on the shape of the network. And it is to be noted that L match network has a unique set of network parameter for a given load and source impedance, wherein the T and pi network have multiple solutions. So please note here that if I want to design a L match network between one load and one source, then you have 1 or 2 unique solutions. Basically two solutions available for L match network. But if you try to design a pi match network or T match network, so there are infinite number of solutions. Now the question is that what is the meaning of this infinite number of solutions? So one of the way to uniquely define or basically determine this matching network or basically designing this a pi match or T match network. So people used to do the Q-based design. Okay, so desired Q design. Okay, so that is one of the way to uniquely define that. But still the question is that what is this other than this Q, other than this, so basically various network having different Q. So other than this, so what is the physical significance of this multiple number of solutions? So these are basically, this multiple number of solutions are basically related to the various phases. Okay, I'll show you later. Okay, the design of such transformer has been extended recently to achieve tunable. So basically, you can see network for tunable components. So instead of a simple capacitor, you can use varactor. Okay, so varactor is basically tunable capacitor. So using that, if you design the matching network, then in that case, you can basically tune for your desired choice. So for example, if you tune for different frequency, or you may tune for different load condition. So because the load condition may vary depending upon the environment. So because of this reason, you can use varactor to make tunable matching network. Okay, so in the distributed topology, you can have single section transmission line. So that is the very basic and fundamental matching network. So okay, most of you are familiar with quarter wave matching network, but not the general purpose complex to real matching network. So that can also be done through single section of transmission line. Or you may have step impedance matching network, or L-type matching network, or single stub matching network, and pi-type or double stub matching network, and T-type matching network. So you have 2 transmission line in the between, so it is well loaded. So I'll discuss this later. Okay. Now, single TL based matching network has unique solution, basically not unique, basically two solutions. Yeah, so I'll show you later on that what are these two solutions. However, the same is not true for the step impedance transformer. So step impedance transformer having multiple number of solutions. Okay, so the similar question arises that in one case you have unique solution, but in another case you have multiple number of solutions. So what are the significance of this multiple number of solutions? So those are basically related to the phase shift of the matching network. Now the question naturally arises, what is the physical significance of such sets of solutions? So as I already discussed that what is this meaning of this? So you have multiple number of solution of the same problem. Then what is the significance of this multiple solution? Okay, so that is basically can be uniquely characterized using phase shift. So the impedance matching network discussed so far are designed based on the quality of matching at the resonance frequency. So quality of matching is basically minimizing the reflection or basically zero reflection. Ideally, it should be zero reflection, but in practice, you cannot achieve that zero reflection. Okay, so that was the mainly goal. Okay, so basically the existing literature devoid the transmission characteristics, especially the transmission phase. So if the reflection is zero, this means basically transmission is 1. If I talk about in the normal scale, then if the reflection is 0, means basically transmission is 1, basically 100% transmission. Okay, and that means basically you will have a 0 dB transmission. Okay, in the dB scale, you have a 0 dB transmission. Okay, that is fine. You have a 0 dB transmission. But what about the phase? You have ever considered that? No. But in some cases, we have seen that phase, that for example, quarter wavelength matching network is provided 90 degree phase shift. So we have seen that one. But still that we have not uniquely characterized that how to design the matching network based on the phase shift. And IMN which matches a real impedance to a real load impedance to a real source impedance or R2R matching network is generally realized by symmetric quarter wavelength transformer, QWIT, quarter wavelength impedance transformer or quarter wavelength matching network, whatever you say, providing a phase shift of 90 degree, phase shift between the input and output. Now, recently, asymmetric type impedance matching network have been used for efficient miniaturization of power divider. Okay, so instead of simple quarter wavelength transmission line, which are basically used in the design of Wilkinson power divider, but in recent year, not recent, basically in year 2007, okay, Dr. Ahn proposed that, okay, we can design those matching network using step impedance matching network. Okay, and she proposed that idea, and okay, so that is good. Okay, so that is good for miniaturization. But still, one of the thing was remain that she does not consider the phase shift. Okay, so but because if you have the same phase difference from the input to the, let's say, one of the output port and another output port, then basically the phase imbalance is basically 0. So that's why it is not an important factor in this case. Unlike quarter wavelength matching network, the transmission phase shift due to such asymmetric structure vary depending upon the choice of the impedances and the value of the electrical length. So please note that. So in this case, it is basically 90 degree, but in this case, it may be something, or not necessarily 90 degree. It can be 100 degree, maybe 45 degree, anything. It will be shown that asymmetric matching network can never be having a phase shift of 90 degree. If you have a asymmetric matching network, real to real, then it cannot be 90 degrees. So please note that here the asymmetric means the electrical asymmetry, not the physical asymmetry. Okay. So sometimes it may be possible a network is physically asymmetric but electrically symmetric. So that is also possible. Okay. So we'll show it later on. Okay. And while the symmetric type real to real matching network always provide a phase shift of 90 degrees. So this is another statement. If the source impedance is real but the load impedance is complex, okay, so one is real and another is complex, then the phase shift deviates from 90 degrees. Okay, so for the symmetric case. So if you have designed a simple transmission line matching network or single section transmission line matching network for complex load to real source, or so for example, real source may be 50 ohm source impedance. So in that case, your phase shift due to this transmission line is basically different from 90 degree. And another thing, please note that. So many people get confused that phase shift angle S21 of a transmission line matching network not necessarily equals to beta L. Please note that. So S21 is not necessarily equals to beta L. So beta L basically represent the electrical length. So beta L represent the electrical length at the design frequency, and S21 is basically the phase shift. So please note that phase shift and the electrical length are not necessarily equal, but sometimes they may be equal. Sometimes they may be equal, but not always equal. So please, this is a very important concept. Okay, so to check what is this transmission phase shift and how this basically different matching network provide different phase shift. So we have designed one, basically you can say some simulation experiment. Okay, so here we have designed one step impedance matching network, okay, which matches a load impedance ZL to matches the load source impedance ZS. Okay, so here ZL has been chosen as 100 minus J30, so it is arbitrarily chosen. So it is not necessarily you can choose anything. And ZS has been chosen as 50. Okay, now so these are the sum of the solution. So these are the sum of the solution. You can get that to design same matching network. So obviously it will provide a matching at the design frequency. All the matching network provides matching at the design frequency. And these are the parameters. For example, you can design a single section of transmission line to match. You can design a single section of transmission line which match the load impedance, this thing 100 minus J30 to 50 ohm. So that is the impedance of this, or characteristic impedance. Characteristic impedance of this line is 76.81, and the length, electrical length 68.69. So electrical length is basically beta L at the design frequency. Electrical length is beta L. Okay, and the total electrical length you can see that is 68.67, and but the angle of S1 or the phase shift is basically 59.04. So this much is the phase shift. Okay, so you can easily see that this beta L and this thing are not necessarily equal. Okay, so please note that. And another design is possible. Let's say you have designed that for ZA is equals to 120 and theta is 10, and then corresponding solution for ZB and theta B is something that is basically 73.86 and 47.68, and corresponding total basically electrical length is 57.68, and this is basically that S21 angle S21 is basically 50 degree phase shift, but the total electrical length is more than that. So there are other solutions. For example, this one. So you can see this is basically more than 360 degree. The total electrical length is more than 360 degree, but the phase shift is 15. 15 means basically you can say that 360 plus 15. Okay, so it is basically 360 plus 15. Okay, because that 360 plus 15 in terms of phase shift is same. Okay, but ideally I should say that it should be 360 plus 15, or you can say 375. And or you can design for 35 degree. So these are various design. Okay, and you can see that all the matching network matches at the design frequency. All that 6 designs are there. So all the 6 design provide matching. Okay, that's fine. But you can see, so it provides different phase shift. So for this design, so for example, design 5 and design 6 provides same phase shift. So design 5 and design 6 provide same phase shift, but these are two different designs. Please note that these are two different designs, but provide same phase shift. So that is also possible. Okay, so you can understand that different matching network provide different phase shift. Okay, that is fine. Now move to so this thing I have already discussed. I am not so importance of transmission phase shift. I will discuss this slide later on. Okay. So before that, what I will try to discuss that basically you have a source impedance, you have a load impedance. So it is a two-port network. So this matching network having some unique ABCD parameter. Okay. So this uniqueness in the ABCD parameter can be defined based on the source impedance, load impedance, and the phase shift. So let's see. Okay, so according to our concept that in matching network S11 is 0, S21 is 1 magnitude, okay, and S12 is basically same as this one, and S22 is also 0, okay. So therefore the total S is basically e to the power minus j pi. So this is the phase shift, or I can write this as 0, and this provide e to the power minus j phi. Phi is the phase shift. E to the power minus j phi. Phi is the phase shift, and 0. Okay. So this is 0. The reflection is 0. The transmission is 1. The magnitude is 1. And the phi is the phase shift or delay. We say the phase delay. Okay. So because phase advance is rarely possible, phase delay is the main concept. Because in any system there is only delay are possible. That advance is basically, you can say, is a kind of hallucination. Phase advance is kind of a hallucination. It is not actually providing any phase advance. Okay. If actually phase advance possible, then you can say that time travel is also possible. Okay. So if phase advance is actually possible, then time travel is also possible. Okay. So delay in time means delay in phase. Advance in time means advance in phase. Okay. So the phase advance, whatever you have seen somewhere, but or you can say the positive group delay or some kind of. So this is a kind of a hallucination, or you can say illusion. Okay. So if you judge it properly, then there is no device is possible that where it provide a phase advance. Phase delay is the only concept. Okay, so let's back to our discussion. So we need to, if we able to characterize this uniquely, that ABCD parameter, also we have know that what is the S parameter. What is the S parameter? And please note that this S parameter. So please note that. So another important concept I'm showing. Please note that this S parameter is basically on reference with respect to ZL. So ZL is one of the port impedance, and with respect to ZS, ZS is another port impedance. It is not basically with respect to Z0. Okay, so please note that this S parameter is basically in relative to port impedance ZS and ZL, not Z0. So this is not. So your conventional idea is basically this one, that Z0. So we terminate both the port by Z0 and get the S parameter. So this is your conventional concept, but for the matching network, it is the right concept. This is wrong. Okay. So when we talk about the S parameter, basically I try to say this one, not this one. Okay. 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 So let's talk to the theorem. Okay. So using this theorem, we can design basically. Ideally, using this theorem, based on this theorem, we can ideally design any matching network with the desired phase shift. Okay, so I'll discuss for some of the simple cases, and then we'll discuss for the few complicated cases also. So, what is the theorem we saying? Okay, a lossless reciprocal two-port network matches a load impedance ZL to a source impedance ZS for maximum power transfer. Provide a transmission phase shift of phi at the design frequency. Then the ABCD parameter of the two-port network can be defined as follows. So that is basically ABCD parameter. So as I told you, for a lossless network, A and D are real and B and C are pure imaginary. And this is defined by H into H is some constant factor. So H value is H is equals to 1 by square root of RS and RL. RS is the real part of source impedance and RL is the real part of the load impedance. And A is basically Zs conjugate into e to the power J5 and real part of this. So if you multiply this and take the real part of this to two complex number, so this is a complex number, this is a complex number. If you multiply them, then if I take the real part, then I'll get the value of A. And similarly, to get the value of D, you have to multiply conjugate of Z into e to the power J5 and take the real part. Similarly, to get the B, okay, so B, so it is basically imaginary part of Zs conjugate and ZL conjugate e to the power J5. Okay, and similarly, C is equals to imaginary part of e to the power J5. So what is the imaginary part of e to the J5? So it is basically simply sine phi. So it is basically simply sine phi. Right. Now, this concept, so you people are already familiar with the ABCD parameter of a transmission line and ABCD parameter of, let's say, quarter wavelength matching network. So let's see. So let's see that so for a real to real matching network, so let's consider that Zs is equals to Z0. Z0 is a real impedance. Okay, so we are considering Z0 is a real impedance, and ZL is also Z0. So I am doing a matching network, real to real matching network, and equal impedance. So I am trying to design a real to real matching network with equal impedance. So same impedance to same impedance, I am doing some transformation. Okay, so that is basically ideally a transmission line. We can show. So this model also predict the concept of transmission line. Now let's find that RS is basically equals to Z0 and RL is also Z, because it is Z0 is real. So for example, you can take it as 50 ohm. Okay. Now what is H? H is basically 1 by square root RS into RL. So if I put this, then y divided by square root of Z0 into Z0. So that is basically 1 by Z0. Fine. H is basically 1 by Z0. Okay. And now what is A? A is basically real part of Z0 conjugate, which is basically Z0 e to the power J pi. Okay, so this is a real number. Okay, and e to the power J pi. If I take the real part, it is basically cos pi. Z0 cos pi. Z0 is a constant, cos pi. Similarly, D is equals to real part of ZL conjugate. ZL is also Z0. It is basically Z0 e to the power J pi. So this is also Z0 cos pi. And C, I have already told you, the C is basically imaginary part of e to the power J phi. So that is basically coming as sine phi. And similarly, D is equals to Z0 into Z0 into e to the power J phi, an imaginary part of that. Sorry, B. B is equals to imaginary part of this. So this is basically coming as Z0 square sine phi. Now if I write this in ABCD format, A, B, C, D, what is coming? This is basically 1 by Z0 into Z0 cos phi J Z0 square sine phi, and then it is coming sine phi, J sine phi, and this is coming Z0 cos phi. And if I rewrite this, so it is basically coming as cos phi Z0 sine phi, sorry, J Z0 sine phi, and J by Z0 sine phi, and then cos phi. So this is the ABCD parameter of a transmission line. It is very well known to you. So where phi is basically beta L. Okay. So this is the ABCD parameter of a transmission line. And for special case, you can always also show that let's say Zs is equals to, let's say, some real number, and ZL is also some real number. Okay. Then in that case, if I want to design for a quarter wavelength matching network or phi equals to 90, then you can easily show it is the ABCD parameter of this is basically it will come as, so I'm not going to the proof, but I can show you that if I consider that if I want to design a real to real matching network, you have a real impedance. Okay, you have a real impedance S, and you have to design some matching network, and then you have real load RL. Then ABCD is basically A, B, C, D. It will come as basically 0, 0. Basically, cos phi is cos 90 is 0, and there here it will be square root of RS RL J, obviously. Then J divided by square root RS RL. So it can be easily proven. Okay. It is not a very tough job, but it can be easily proven. So you can understand that this theorem is very useful to understand the phase shift of matching network. Okay, so because it provides the ABCD parameter, and another thing is that as the concept of you can say that how can I say, the phase shift and the source impedance and the load impedance, all the things are there inside the equation. Okay, so therefore whatever was not possible with the S parameter itself, but with the ABCD parameter you can easily make any kind of design. Okay. So I'm not going into the proof of this theorem, so we can skip this. So let's do some example. Okay. Do some example that how to design simple matching network using this concept. So for example, let's consider that you want to design a T match network. So this is a reactive element. So that's why reactive series element, and reactive shunt elements. It means basically susceptance, and these are two reactants. Okay, this is one reactance, this is another reactance, and this is one susceptance. Okay, so as you people are already familiar that how to compute the ABCD parameter of a cascaded system. So we can say that one series section cascaded with one shunt section and then cascaded with a series section. So you have a series. So for a series, it is basically 1, 1, diagonal 1, and in the non-diagonal you have Z. Okay, so this is basically Z, okay, or the impedance. So here the impedance is basically JX1. And similarly, you have a shunt section. So for shunt section, you have these two diagonal are 1, okay, A and D are 1, and you can say the C is basically equals to Y. Y means basically JB3. And B is basically equals to 0, okay, for a shunt element. And similarly, for another series element, you have the diagonal A and D both are 1, and B is basically Z2, or you can say JX2, and C is basically equals to 0. Okay, so if I do multiplication, then finally I will get that A is equals to 1 minus x1 b3, D is equals to 1 minus x2 b3, and C is equals to b3, and B is equals to x1 into x2 minus x1 x2 b3. Okay. So you can see that A, D, B, and C all are real numbers. Okay, so all this small quantity are basically real number, but here in this case, this B is purely imaginary number, this C is purely imaginary number. Okay, and A and D are pure real number. Okay, now using this equation, we can easily find out the value of x1, x2, and b3. So if I compare this, I can easily say that b3 is basically equal to C. If C is known, then I can easily find out that what should be the desired b3. Okay, if A and D are also known, then I can easily find out what is the desired x1 and x2. Okay, so here in this equation, if I plug in the ABCD parameter, of phase matching network, then I can easily find out that what should be the value of B3, what should be the value of x1, and what should be the value of x2. Okay, and once I get the value of this susceptance, this reactance, and this reactance, I can convert them into some realizable inductor and capacitor. Okay, so let's see one example that how this procedure work. Okay, so for example, this is the problem. Design a lumped T-match network which matches load impedance of ZL equals to 100 minus J30 ohm to a source impedance of internal, to a source having internal impedance ZS is equals to 50 ohm with a transmission phase shift of 60 degree. So it should provide a 60 degree transmission phase shift, and you have to design at 1 gigahertz frequency. So for this problem, RS is equals to 50, XS is equals to 0 because it is a real. Okay, RL is equals to 100 and XL is equals to minus 30 and phi is equals to 60. And based on this data, I can easily calculate the ABCD parameter of the desired matching network. So that is coming as A is equals to 0.35, D is also 0.33, B is coming J 71.84 and C is coming J 0.0122. Okay, so you know the ABCD of this matching network, desired one. Okay, now you have to realize this using some lumped element. So for example, using some inductor and capacitor. So how to do that? So at first you have to find out the desired susceptance and the reactance. Okay, so desired reactance has been found and desired susceptance has been found from using this following formula. Okay, so B is equals to B3 is equals to C, X1 is equals to 1 minus A divided by C, X2 is equals to 1 minus D divided by C. Okay, so you can see that that unit of this X1 is basically in ohm and B3 is basically mho or basically Siemens. Sometimes we write this as Siemens. Or in general, the order of basically susceptance is in millisiemens. Okay. In most of the cases, it is in millisiemens. Okay, and this is basically in normal, basically in ohm. Okay. Okay. So here, what you can see that this is a positive reactance. Positive reactance means it is an inductor. So positive reactance means it is an inductor. So this is also positive reactance. It is also an inductor, and this is a positive susceptance. Positive susceptance means basically it is a capacitor. Okay, so you can see this will be a capacitive element, this will be inductive element, this will be an inductive element. Okay, now I can easily find out the value of the capacitor, inductor, and this in two inductor L1 and L2 and capacitor C3 by B3 divided by omega naught. So 2 pi f naught is the omega naught, and similarly L1 is equals to, this would be X1. Okay, so this is a printing typo. This would be X1 divided by omega naught. Okay, and similarly L2 is equals to X2 divided by omega naught. Okay, so and based on this you can easily find out that your capacitor is coming 1.95 picofarad and 8.40 nanohenry, and this is basically 8.58 nanohenry. Okay, so so before going into the next pi type network, okay, so I'll show you one of the tool actually which is I am currently developing, that is a multiport designer. Okay, so it has many features, and currently I am also incorporating the impedance matching network design feature also. So here I want to design for a single band design, and type of network is lumped T network, and design frequency is 1, ZS is equals to 50, and ZL is equals to 100 minus 1J into 30, and phi is equals to 60. Okay, so if I put design, so it will design automatically design. So it is coming that this is basically 8.4 nanohenry, it is 8.58 and 1.95. So let me check these values are matching or not. Yeah, it is coming correct. Okay, so it is 1.95 picofarad, it is 8.40 and 8.58. Okay, so this is the circuit diagram. So here you have the source impedance, and you have the source voltage source, and it will have some source impedance, and you have a inductor. So this basically inductor at first convert some portion of this impedance into some reactive component is added, and then again this reactive component basically subtracts some of the reactive element, and finally this reactive component finally subtract all the reactive component. This basically became a real impedance. Okay, so this is the design part, and let's do the analysis. Something is going wrong. Okay, so let's do it for 100 ohm. Okay, so here you can see that at the design frequency 1, it is basically perfectly matched. S11 is basically goes to basically very low, okay, in terms of dB, very low, and the magnitude of S21 is coming 1. Okay, so it is almost 1. Okay. So 10 to the power minus 6. So if you zoom in and make it very close, then you will get it is basically almost exactly 1. Okay, at that design frequency 1 gigahertz. And if I look at the phase, okay, so I have designed for 60 degree phase shift. You can see that at the design frequency 1 gigahertz, it is providing a phase shift of 60 degree. Okay, at the design frequency 1 gigahertz, it is providing a phase shift of 60 degree, minus 60. Okay, so next we'll try to design, yes, find out. Okay, so next we try to design a pi matching network. So the design principle is same. At first we need to find out the ABCD parameter of the pi network, and okay, and from that I need to find out what is the required reactance and the susceptance. Okay, and if you do so, so let's how to get that. So you have a shunt element, then you have a series element, then shunt element. So if you multiply this, then I will get that A is equals to 1 minus x3 b2, and B is equals to 1 minus x3 b1, and C is equals to b1 plus b2 minus b1 into b2 into x3, and B is equals to x3. Okay, so you can easily find out that x3 is basically equals to B. Okay, and B is equals to 1 minus D divided by B, and B2 is equals to 1 minus A divided by B. Okay, so using this concept, you can easily find out the value. Okay. Okay, so next problem is design the same matching network using pi match network. Okay, so the same matching network I am trying to design using pi match instead of T match. Okay, that load impedance is same, source impedance is same, and the phase shift also same. The network will be pi type network. So for that, at first I have calculated the ABCD parameter, what is the desired ABCD parameter and the design frequency. Then I converted this desired ABCD parameter into reactance and the susceptance. And then later on, this reactance and susceptance are converted into, so this is a positive reactance. Positive reactance means inductor. Okay. And then it is a positive susceptance means capacitor. This is also positive susceptance means capacitor. Okay, and you can see it is basically consists of 2 capacitor and 1 inductor. Okay, so this is the matching network, and it provides a phase shift of 60 degree at the design frequency 1. Okay, so let's do this again. So 100 minus J to 30. This is 60, and this is pi match. So pi match basically look like this. So 1 design frequency, this is 50. Then it is 100 minus 1J to 30. Then you will have 60 degree. Let's do the design. So this is a pi match design. Okay, And analysis part I am not doing for this one because some error is there, so that complex part has not been implemented yet. So let's do the analysis part for the 100 ohm. So let's make another design, do the analysis. So you can see at the design frequency it provides a phase shift of 60 degree. Okay, and let's see the amplitude response. So at the design frequency it is perfectly matched. Okay, and provide a transmission of 1, transmission of basically 0 dB, transmission of 0 dB. Okay, so you can see that is basically provide a transmission of 0 dB. Okay, at the design frequency, and the reflection is 0. Total reflection is 0 in the normal scale, but in dB it is very low. You can consider that basically this depends upon the computer epsilon level. Let's say in 10 basically minus 350 dB. Okay, something like that. So ideally it should be infinity. So if you do that analytical calculation, so 0 means if you convert into dB scale, so that is basically coming out minus infinity. Okay, so next is the L-match network. So L-match network is one of the very popular network. Okay, so L-match network is one of the very popular network. So I'll show you that this L-match network are nothing but a special case of T-match network or pi-match network. How? If I put that x1 is equal to 0. So this reactance becomes a short circuit. If I put x1 is equal to 0, this reactance becomes short circuit. Then it will look like a L. And in the other word, we can say that a value of this network is equal to 1. So we can see later on. Okay, so that how this if you do some simple calculation of this shunt element into series element, then a value will come 1. And in the other way also we can say that in this case it basically, if I put that B2 is equal to 0, so what does it mean? That B2 is equal to 0 means basically it is an open circuit. Okay, so you have a susceptance 0 means basically open circuit. So open circuit having susceptance 0. So therefore this is basically not available, so open circuit, so it basically look like a L-match network. Okay, so and in that case also you can say that A is equal to 1. So from our principle that we understand that if A is equal to 1, so therefore the phase is very unique. If A is equal to 1, then phase is very unique. Okay. So the L-match can only provide 2 distinct phase shifts. The L-match network you cannot implement any phase shift. Let's say you want to implement a phase shift of 60 degree or 90 degree or maybe 120 degree, but you cannot use L-match network. So L-match network is incapable. Why? Because it has a one phase shift element. So basically the shunt element are the main phase shifting element. So please note that only the shunt element are the phase shifting element, the series element are not. Okay. So you have only one phase shifting element. So therefore you have only one step. Okay. But in this case you have 2 phase shift element. So in this case you have 2 phase shifting elements. So therefore it has multiple number of states. Okay. And though it has that T-match having one phase shifting element, but this provide a control. This providing a control to this phase shifting element. This provides some control that this phase shift can be controlled using this series element. Okay, so that this series element actually provide the control to this phase shifting element. Okay, so that's why that T network provide multiple, and any kind of phase shift you can implement using T network. Now this unique phase shift can be calculated based on this formula. So I'm not going into details into this formula, but this L-match network can only be realizable if RS into RL is less than mod of ZS. Okay, so let's say, for example, I want to design a matching network for ZS is equals to 50 and ZL is equals to 100. Okay, so let's check the condition. RS into RL, so that is basically coming as 500. 5,000. Okay, 5,000. So whether this is greater than, so I have to check that this should be greater than, sorry, this should be less than ZS. Whether this is less than mod ZS square. So if I put so this is RS RL and mod ZS square, so that is 50 square, then 50, this is 25, and then 0, 0. So you can easily see that this is basically less than. So basically mod ZS square is less than RS RL. So therefore you cannot implement a L match network for this design, but you can use the inverted L match network. So I'll show later on. So what is inverted L? Okay, so inverted L match is something like this, that it is basically ulta L. Okay, so the reverse L. Okay, so you can see that it is basically mirror image of L. Okay, so and if I rotate this, so it look like a L. So if I rotate this network by 90 degree, okay, then it look like a L. Okay, but in this case, it look like inverted L. So in this case, it is also a special case of T match network and pi match network. So what is the special case? That is, if x2 is equal to 0, or basically this is short circuited, then it look like a inverted L. Or in this case, let's say if I say that if it is B, in this case if B1, okay, so if B1 is equal to 0, or if it is open circuit, then also we can say it is a basically inverted L match network. Okay, so and the condition here is basically D equals to 1. Okay, so if I D equals to 1, then we can say that the phase shift of the inverted L network also fixed, and there are two distinct shifts. Okay, so this can be calculated from this complicated formula. I'm not going into the details of this complicated formula, but provided this, it should satisfy this condition. But RS into RL should be less than mod of ZL. So if this condition is satisfied for this impedances, okay, that RS into RL is basically less than mod of ZL square. Mod of ZL square is how much here? So mod of ZL square, you will coming that 100 square, then equals to 10, 1, 2, 3, 4. So 10,000. Okay, so you can say that RS RL is 5,000, but it is 10,000, so it is less than that. So you can use inverted L match network for this purpose. Okay. No, I am not going into this design. So let's see that one special case that, let's say, for example, I want to design a matching network from 50 to 100. And if I provide a phase shift of 45, okay, then it is basically inverted L matching network. Okay, so as I told you that in this case, only inverted L matching is possible. Let's see design. So it is the inverted L match. So something is wrong. Analysis part, and let's see that if I design for minus 45 means 360 minus 45 means 315. So that is another design. So this is another design. So you can see that it is also an inverted L match network. Now if I do the reverse, so this is my source is 100 and load is 50. Then if I design, then you can see is a basically L match network. Okay, so in this case it look like a L match network. 5 design, so you can see it is a basically L match network. Okay, so that's it from this part, and now we'll move into another special type of matching network, that is symmetric, a special class. Okay, so the matching network are basically can be broadly categorized into two parts. That is basically symmetric matching network. So obviously that is a subset of general asymmetric matching network, because symmetry is special case of asymmetry. Symmetry is special case of asymmetry. Okay. Now to design this asymmetric matching network, design this symmetric matching network. So what should be the phase shift? Okay, so that can be easily derived by providing the condition that A is equal to D. for a symmetric network that A is equals to D. If I put okay, so if you put A is equals to D, then I can get the condition of the phase shift. So what should be the phase shift for which the network should be symmetric? Okay, so that can be done by equating A and D. Okay. Now this is the lemma. A symmetric matching network which matches a load impedance to a source impedance provide a phase shift of phi. Then phi is equals to tan phi is equals to RL minus RS divided by XS minus XL. So if I take the tan inverse of this, so obviously this tan inverse having two value. This tan inverse having two value. One is whatever that minimum one, and then 180 plus that one. 180 plus that one. So these are the two value. Okay, so I'm not going into proof. Okay, so next is constant phase shift circle. Okay. So now for this symmetric kind of matching network, okay, for the symmetric kind of matching network, so let's say this line that phi equals to 90, so which is basically represent real to real matching network, real to real matching network. So you can see, so this is a basically line. This is a line. So you can say that all the real impedances are basically lying on this point. All the real impedances are basically lying on this plane. And from this you can say that if you design any real to real symmetric matching network, so any real to real symmetric matching network, it will provide a phase shift of 90. Now for, let's say, this impedance. So if I want to match this impedance to the center means 50 ohm. So for example, we are considering that my base impedance is 50. Okay. So if I want to match this impedance, so this impedance point is basically in the reflection plane. So this is speed chart plane. So speed chart plane means reflection in gamma plane. Okay. So in the gamma plane, so I have an impedance here. I want to design a matching network which matches it to the 50 ohm. Okay, and the matching network should be symmetric. So in that case, I need a phase shift of 60 degree. So it is always true. Or I need a phase shift of 180 minus 5, or basically 120. So either it should be that 5 or 180 minus 5. Okay. Next is single section matching network. Okay, single section transmission line matching network. This is another very important matching network, but in most of the EG or PG course, they don't teach this one. Okay, this matching network. I don't know why, but this matching network is basically related to the quarter wave transformer. Okay, so that is the special case. Real to real matching network is quarter wave transformer, but other cases. Hello?
Someone is talking. Please stop your microphone. Please, participant, please stop your microphone. Mute your microphone, please.
Okay, so this is a special type of matching network. It is very simple. One of the things is it is very simple. Okay, the characteristic impedance of this matching network can be found out using this formula. I am not going into the details how this formula is coming. So, but you can easily derive this formula. Okay, so based on this formula, you can easily find out the characteristic impedance and the electrical length of the transmission line, a single section transmission line. Okay, and why this is very important? Because it provides you the basic understanding of the matching network, how the matching network work, okay, and what is the difference between the phase shift and electrical length. So those concepts can be clarified from this single section matching network. And the special case of this matching network is basically real to real matching network or quarter wave transformer. Okay, so if my load impedance and source impedance both are real, so under that condition, we can easily show this theta is basically coming out to be 90 degree. Okay, so it is basically 90 degree or basically 270 degree. So it should be 90 degree or 270 degree. And this ZC is basically square root of RS into RL. Okay, so it can be easily proven. Okay, so this type of matching network, so that symmetric transmission line matching network, only matches a specific area in the speed chart. So it only matches only specific area. So if your impedance is lies in the shaded area, okay, if your impedance is lies inside the shaded area of this Smith chart, then only you will able to match using single section transmission line. If it is outside this shaded area, then you will not able to match using single section of transmission line. So what is the solution for this? The solution has been provided long ago by C.T. Tai. Okay, the solution has been given. So these are basically, I have reproduced the work of C.T. Tai and Dr. An. Okay, so mainly the original concept was proposed by C.T. Tai, and later on, basically, I can say that Dr. An basically reinvented that. Okay, but the original idea was proposed by C.T. Tai, a single section transmission line, and you can easily find this literature in basically it was published in Journal of Applied Physics, JAP, I think 1954 or 56, around that. Okay, so another concept is that constant impedance circle. Okay, another concept is constant impedance circle. Okay, so if you have a single section matching network, then the constant impedance circle are basically, if you consider that, let's say this is 1. Okay, so your normalized impedance is 1, then, or you can say if your this thing normalized impedance is 50, then ZC is equals to 100. 2 into 50, this 100 basically represent this line. So all the impedances lies in this circle can be matched with 100 ohm line. So all the impedances lies in this point can be matches with 100 ohm line. Okay, and all the impedances with, let's say 250, said that this one. Okay, so all the impedances in this point, in this dash point, then can be matches with a line of line impedance 250. So you can see that as I going far away from the center of the speed chart, very far away from the center of the speed chart, then you need a very higher impedance to match it to the center. Okay, you need very higher impedances. So that is one of the conclusion. Another concept is constant electrical length curve. Okay, so another concept is constant electrical length. So for example, let's say if you have a 90-degree line. Okay, so all the line are 90 degree, but obviously the impedances are different. Okay, so all are 90-degree line or the quarter wave line. So if you have a quarter wave line, then all the real impedances. So this in the speed chart, this line basically impedes all the real impedances. Okay, so they don't have any complex part. So all the real impedances can be matched using quarter wave length transformer to the center. And if let's say I want to choose the 60-degree line, so then all the impedances are there in this dotted line. Okay, can be matched with a line length of 60 degree. Obviously, for different position, the impedances are different. Okay, so if I superimpose this and this one, if I superimpose this chart, and this chart, then you can find out what should be the characteristic impedance and what should be the electrical length. So that can be easily find out from that kind of split chart. Okay, so obviously this is a kind of modified split chart. So we are basically, instead of real, basically a constant VSWR circle or constant resistance circle, constant reactance circle, we are also providing the constant impedance circle and constant electrical length circle for single section of impedance matching network. Okay, so this part basically goes to single section of transmission line. So the solution for this, I have not included this slide in this here. So the solution for this, if you want to match outside this, so you need to make a parallel transmission line matching network. Okay, so if you want to make matching here in this portion, then you can make parallel section of transmission line. So you have a two parallel transmission line, and if you try to design a symmetric matching network for this, for a certain load and source, then you can easily obtain the matching network. Okay. So I'm coming to almost the end. So that is asymmetric type of matching network. So this type of matching network in this class, so we'll mainly discuss about the step impedance, asymmetric T, asymmetric pi. Okay, so this is basically asymmetric. You can see that this is the two transmission line section are there. So this is one section, this is another section, and here one section is there, but it is loaded asymmetrically at a not at the center. This loading. So this loading is, it may be a capacitive loading or maybe inductive loading. Okay, so it may be a shunt. So here we are only considering the shunt case, not the series case. So it may be shunt stub or maybe a lump capacitor or lump inductor. Okay, and here in case of pi match, so you have one center line is there, and in both the side you have two stubs are there. So maybe capacitive or maybe inductive, which depends upon the basically the phase shift of the matching network and also the load impedance and the source impedance. So the step impedance matching network design. So as I told you, the rule is basically you have to at first find out the ABCD parameter, and from the ABCD parameter you have to find out the design equation. Hello. Do you have any question or query?
Hello, sir.
Yes. Hello. Am I audible to you?
Yes, sir.
Okay. Is there any doubt? Okay. I am proceeding. So this is the design equation. So I'm not going into the design equation. So how basically you know that how to derive this one. So if you do by yourself, then that is basically more better instead of looking into this equation itself. Okay. So what is the implication and how this result can be interpreted? So for this, what we have chosen, that load impedance has been chosen as 100 minus J30 and source impedance as 50. Okay. And we want to find out that where the solution exists. Okay, so and we have considered that phi vary from 0 to 360 degree. The phase shift vary from 0 to 360 degree, and ZA, the impedance of the first line. Okay, so ZA means basically impedance of this first line has been chosen in between 20 ohm to 120. So in this between it can vary. So where the solution region lies. Okay. Now, to find out the solution, we are at first find out what is the possible value of ZB. Okay, so you can see that this color graph, this color map basically shows the position or point where it is having a different value. For example, very darker means very low impedance value. So this is also not practically realizable, and this lighter one is very high impedance value or almost close to 120. So these are also not good. So in between this yellow region, if you try to find a solution in the yellow region, then that is very good for the design purpose. Okay. Then it comes to the theta. Okay, total electrical length. So what is the total electrical length of the line? Okay, so if you want to find a electrically small, okay, if you want to find a electrically small design, okay, so obviously for miniaturization purpose, you need to find a electrically small solution. Then you should go to in this region. In this region, you can see that it is basically electrically very small. So this is 80. So you can say this is coming around basically 35 or 37 around that. Okay, so in that region, if you try to find out any solution, then it is a basically electrically very small step impedance matching network design. Now, next interpretation is the asymmetricity factor. Okay, so asymmetricity K. What is K here? So K is basically one factor based on this basically how this what is the means basically the ratio of this length and this length. Okay, so somehow. Okay, so somehow this K, the K basically vary when K is equals to 0.5. When K is equals to 0.5 means basically this symmetric. It's same length. So it has whatever the same length and whatever the length, that this length are same. Now you can see this line basically indicate the this line and this line basically indicate the matching network which are basically can be implemented using single section of transmission line. This line and this line. Okay, so please note that. So we basically repeat after 180 degree. So this line repeat after 180 degree. So this line is coming around 60 degree and almost close to 60 degree, and then this again this line is coming around basically 180 plus 60, whatever that is, around 240 something. Okay, and so this basically 0.5, this 0.5 representation of this 0.5 means basically here your length of the first line and length of the second line are equal. Okay, so and other cases one is extremely small. So if it is 0, one of them is extremely small and another is high, and in this extreme position 1, so it is another, so one of them is basically extremely small and another is extremely high. So for example here, so if k is equals to 0 means this line is basically almost 0, so no line is there. Okay, or if k is equals to 1, then this line is not there, only this line is there. Okay. Okay, so the next design is asymmetric T network design. So the design rule is same. So at first we determine the ABCD parameter. From the ABCD parameter, we have determined the design equation. Okay, so here also we have chosen the load impedance is 100 minus J30 and source impedance is 50 ohm. Okay, now here it shows very interesting result. So it is basically this graph is basically showing the length of the stub. This graph is showing the length of the stub. So you have a stub here, stub is connected, and the length of the stub when it is 0. When the length of the stub is 0, it's basically indicated single section of transmission line. So these 2 points, so this point and this point basically indicate single section of transmission line. And the line going through this point, is basically indicate the solutions of symmetric matching network. The line going through this point, the vertical line going through this point is basically represent the solution of basically symmetric matching network. Yes, whatever this line. Okay, and here whatever the line also going from this point is also basically represent the solution of symmetric matching network. Okay, and when this is too high, the length of the stub is too high, almost close to 90 degrees. So this is basically not a good region to choose. So these are not very good region to choose. So but good region lies between here or here. Okay, so here also we'll see later on. Okay, that it should be find out from the total length. Okay, so the total length of this line, the total length means basically this length plus this length. Okay, length of this line and length of this line, the total length. So this basically reflect the miniaturization. Okay, now if you find out the solution here in this region, okay, so if you find out the solution in this region, then you can see that that a good basically miniaturization is possible. So you can see that almost it is coming around 35 or around 40. Okay, 40 with 40 degree electrical length line, you can match this impedance to this one. Okay, so that is basically better than single section of transmission line. So single section transmission line solution is here. Okay, so it will come around 60 something degree, 65 or something. I cannot exactly recall, but it will come 69 or something like that. Okay, so next is asymmetric factor K. So it's basically represent the asymmetricity. So this line represent the symmetric matching network. Okay, so this line and also this line. Okay, this line and this line basically indicate the symmetric matching network. And you can say that if K is extremely low. Okay, so if K is very extremely low, so here, okay, so extremely low is, extremely low here. So in this section, so this basically represent almost single stub matching network. Okay, so when K is extremely low, it's basically single stub matching network. Or K is extremely high, so that is also single stub matching network, but the position of the stub is maybe in one case source side and in one case it is in load side. And here is the bandwidth. Okay, so we have studied about the electrical parameters. So what are the different choices of electrical parameter are possible based on the design? Okay, so that is fine, but in some application we don't want only miniaturization, we want a good bandwidth. Okay, a good bandwidth is possible. So for that, if we vary the parameter, and we can see that for step impedance matching network, okay, for step impedance matching network, a good amount of bandwidth can be possible. So almost 120%, almost 120% bandwidth is possible if I choose the solution from this region. If I choose the solution from this region, then we can get a very good bandwidth. Okay. Similarly, for asymmetric T matching network, if I choose the solution from this region, then also we can get a good amount of bandwidth using asymmetric T matching network. Okay. So these are some of the experimental results which I performed during my PhD. So that is long back, around 2016. So what we have designed, so we have chosen among this different topology, you have chosen the asymmetric T topology because it is one of the things is very easy to design, and another thing is basically we don't have much complicacy in the design. Okay, so here this is one L section. Yes, this is one L section. This is this is one transmission line section. This is another transmission line section. Basically, it will be implemented on Microstrip, and this is the stub line. Okay, so this is the length. So basically, this impedances can be converted into width. So as some of you may be familiar with Microstrip technology, that in Microstrip technology, the characteristic impedance is basically converted into trace width. Okay, and the electrical length are basically converted into physical length, okay, at the design frequency. So you can see, so this L and W are basically obtained from this electrical parameter. Okay, so basically ZC or basically here ZM, and here 50 ohm line is chosen for example for 50 ohm. So it is for example, let's say for 50 ohm, if you have a FR4 substrate of height 1.58, then the width of the line is around 3 millimeter. And similarly, if you have, let's say, 100 ohm, then it will come around 0.7 or something like that. I cannot exactly recall. So maybe something like that. Okay, so that is basically width. Width is basically scale from the characteristic impedance, and the length is basically scale from the electrical length. Okay, so this scaling has been at first done, and then later on you need to do some tuning. Okay, because of this effect. Okay, so because of this, you can say discontinuity effect. Because of this discontinuity effect, it does not behave like an ideal transmission line. Okay, because of this discontinuity effect or sudden discontinuity, so it does not behave like an ideal transmission line. So therefore, you need to do some tuning. Okay, so the initial guess should be find out from the electrical length and the characteristic impedance. So that is the initial guess. So this, so we have designed for two cases. One is broadband and another is 45-degree phase shift. Okay. So these are the following characteristic impedance and the electrical of the main line and the stub, and this is the asymmetry factor. So if I know asymmetry factor, I can find out what is L1 and what is L3. Okay. And then this line, as I told you that this impedance, how much? This 82.1. 82.1 has been converted into how much? That is basically 1.15. Okay, so 82 converted into 1.15 millimeter on FR4 substrate, height of 1.58 and directly constant 4.4 and loss tangent 0.02. Okay, and you can see that for 50 ohm it is coming around 3. Okay, so 50 ohm line means width is 3, and L2. Okay, so you can see that L2 length of the stub here is, it has been calculated based on the electrical length. Okay, so more electrical length is more longer stub. Okay, small electrical length is smaller stub. Okay, and similarly here W1 is coming 0.7, so it is basically corresponding to 0.7 is 100 ohm. As I told you that for 100 ohm it should be 0.7. So yeah, I was correct. Okay, and so these are the measurement or physical dimension we have obtained. Okay, so after if you convert this into, so any standard, you can say that Microstrip calculator available on the internet, or you can write your own code to convert this physical length and electrical length and the characteristic impedance with the width and basically physical length. Then you can easily obtain this data. Okay, so obviously this data we have little bit tuned it, so it is not exact. Okay, because One of the thing is that you cannot exactly get, because of that basically discontinuous peak. Okay, so these are not ideal transmission line. Okay, so these are basically practical microstrip lines. So you will not get exact ideal result. Okay, and after designing, so we have compared the circuit simulation result, full wave simulation result, and the measure result. So those are basically quite matching to each other. And one of the important factor is the phase shift. So you can see the phase shift is coming exactly same, almost same. So only few point something is difference. So you can say that circuit simulation result, full wave simulation result, and the measure result all are basically matching to each other. Okay, and you can say that in the high frequency there are some certain dip in the, you can say, in the measure result. So that is mainly due to the lossy or substrate. Okay, so maybe the loss on the substrate or loss in the connector may be also possible. Okay, so you can see there is a dip here. And you can see that a quite broadband matching has been possible, but please note that the center frequency, the center frequency of this broadband has been shifted. Okay, so please note that I have designed, so here it is perfectly matched. I have designed for here, it is perfectly matched. But in the other frequency also it is getting matched. So if you try to center it, in the middle, so what you have to do? You have to scale the line length. So if you do the electrical length scaling, then you can shift this, you can say the 2 gigahertz center frequency. You can shift this 2 gigahertz center frequency into 1 gigahertz. Okay, so that is possible. Okay, so this is another design. So that is for 45-degree phase shift. And here you can see that at the design frequency 1 gigahertz, you have a 45-degree phase shift. Okay, and also it has a good match. It has a good match of, let's say, 40 dB in the measure result. It is that the resonance has been little bit shifted from the deviate from the design frequency, but it is quite good. The result is quite good and promising, and you can see that it provides a you can say that transmission of less than 0 dB. So it is coming around 0.1 or 0.5 dB or something like that. I cannot exactly recall what is the measured value, but it is not basically 0 dB. It is less than 0 dB. Okay, so that is because of some of the radiation loss and also conductor loss, connector loss, dielectric loss, various losses in the practical scenario. Okay. Okay, so in the conclusion, so what I can say, that concept of transmission phase shift and importance of okay, so before going into conclusion, so as I promise you, so when this transmission phase shift is important, so that thing I need to discuss. Okay, go to that slide. Okay, so if you are designing a single matching network, then there is no need to consider the phase shift. You don't need to. But if you are designing multiple number of matching network, then you should have. Okay, why? Because, for example, consider a 2-element phase array. So you have one antenna 1, and antenna 2. Okay, so antenna 1 having impedance of Z antenna 1, antenna 2 having impedance of Z antenna 2. Okay, now I have designed without knowledge, so we have designed 2 single stub matching network. Okay, so when we design single stub matching network, we don't have any knowledge of phase shift. Okay, so we have designed this one and this one. Now this matching network provide a phase shift of, let's say, 60 degree, and this matching network provide a phase shift of 90 degree. So you can see, so there is a 30 degree imbalance in the phase. So you can see there is a 30 degree imbalance between these two phases. So therefore, the main beam will not point in the broadside direction. Then the main beam will tilt a particular angle. Okay, so then the main beam will tilt it in a particular angle. Okay, so that's why you need to consider the phase shift concept when you are designing multiple matching network. For this is one kind of example, and another example, and this example actually I have pointed out error in one of the paper of Wang and Wu. So there they have designed a quarter wavelength matching network. Okay, so quarter wavelength you can say quadrature coupler. They have designed a quadrature coupler with different impedance, port impedances. So they have designed for different port impedances. Now you can, if you think that this matching network provide a phase shift of phi 1, this provide phi 2, this is phi 3, this is phi 4. Okay. Then when we design this quadrature coupler, provide a phase difference between port 2. So if I excite at port 1, between port 2 and 3, so there should be 90 degree phase difference. Now, under this condition, you can say the phase difference between port, if I excite at port 1 and the phase difference between the signal coming at port 2 and 3, so it will come around 90 degree plus additionally, you have phi 2 minus phi 3. So you have 90 degree plus phi 2 minus phi 3 or phi 3 minus, so whatever the difference you are taking. Okay. So basically the difference between phi 2 and phi 3. So whatever the phase difference between these two, so that is basically an additional factor. So if you don't have that knowledge, then it will lead to a erroneous design. Okay, so that is not a good design. Okay, so let's conclude this session. So concept of transmission phase and its impedance and its importance in design of matching network has been discussed. Okay, a general set of network parameters of impedance matching network have been derived and incorporating the transmission phase shift, and there exist two distinct phase value. So basically they are 180 degree apart for a given source and load impedance for which the network is symmetric. Symmetric means electrical symmetric, not necessarily physical symmetric. So it is possible that physically asymmetric network provide electrical symmetry. So that is possible. Okay. And the symmetric matching network, however, cannot provide arbitrary phase shift. So please note that if you design a symmetric matching network, then it will provide a particular phase shift. So there are two possibilities. It cannot provide any arbitrary phase shift, but asymmetric matching network provide any arbitrary phase shift. Okay. By incorporating transmission characteristic while designing matching network, one can simultaneously match as well as provide a appropriate phase shifter. So what we concluded that you don't need to design a phase shifter differently. You don't need to design the matching network separately. So you can design both phase shifter and matching network on a same circuit. So that's all. And if you have any question or query, please let me know. So I'll be glad to answer all the questions.
So all the participants, so we are requesting if have you any queries, please feel free, you can ask. So our expert is available.
Hello, sir.
Yes.
Am I audible?
Yes.
Sir, I want to ask that normally in a transmission line, when it is not matched, we are using either quarter wave line or a single stop or a double stop. How it is different from the this matching methods from that?
Okay. So one of the things is that, okay, so I'll show you that how that original way of how you design the matching network. For example, I want to design a single stop matching network. Okay, so let me. Okay, so let's say series stop. Okay, single stop matching network. So what we are doing? So at first, we are trying to find out the position where your impedance is basically 1 plus jx. Okay, so where your impedance is 1 plus jx, and you basically by using open stub or short stub, so basically you are cancelling out the x part. Okay, so in this way it is done. But here you don't know how much is the delay. How much is the delay due to this stub? How much is the delay due to this transmission line? So you don't know. Even if you calculate the electrical length. So for example, if you calculate the electrical length, let's say this line is coming around, let's say 60 degree. So beta L is 60 degree. So can you say this is the phase shift? So no, so that is not the phase shift. Okay. So in in the conventional way of designing, so they don't consider the phase shift. They don't bother. Because in most of the cases, they try to design a single matching network or designing matching network for identical load and source. Okay, so in that case, it does not matter. Okay. But if you try to design for different load condition and different matching networks, in that case, it is very important to take care of the phase shift. I hope it is clear. And if it is not, then I will try to make it more clear.
Sir, then which one is more accuracy, that conventional method or this network using matching?
Pardon?
Which one is more accurate, sir?
Hello?
Sir, I want to say that in this method, it's
Hello?
more accurate. Hello?
I think there is some issue with bandwidth.
Hello.
Am I audible, sir? Am I audible?
Hello.
Yes.
Sir, I want to say that then which one will be the more accurate? More accuracy. Okay.
Hello?
Hello? Hello, sir. Am I audible, sir?
Okay. Am I audible, sir? Hello.
Yes, sir. You are audible.
Yeah, you are audible, but your voice is a little bit breaking. Okay, anyway, I can hear it.
Actually, a participant asking stub matching or this phase shift matching. So, which one is better?
Low bandwidth. Hello?
Yes, sir. You are audible, sir.
Yes.
Actually, sir, participant asking which one is better? Maybe stub matching, single stub, double stub matching.
Which one is better? So it depends upon the application, as I told you, na.
Okay, sir. Okay.
It is depending upon the application. If you try to design matching network for multiple, if you are designing multiple matching network, then you should consider the phase shift. Otherwise, you don't need to.
Only for the multiple network.
And
most useful.
I will say that considering the knowledge of phase shift is important, and I think that is better compared to the conventional design. Compared to the conventional way of design, so considering the phase shift is better, because that will provide you more insight that what is happening.
Okay, sir.
So
okay,
from
sir.
the conventional design, you don't have any awareness of the how much is the phase delay.
Okay, sir.
Am I audible?
Yes, sir. Sir, next question, sir.
Okay. Any other question?
Yes, sir. Other question. In one slide, sir, you have shown that shunt elements are using for the phase shifting element, not series. Why, sir?
Let my video off. Then I can.
Sir, I'm repeating again.
Stop sharing. Yeah, but still your voice is a little bit breaking. Okay, anyway, I'm a little bit able to hear you.
Sir, I want to say, again, I repeating question, sir. I want to say that you have explained that the sound elements are normally used for the phase shifting elements, not series elements. So I want to say that why?
Yes.
Are you getting, sir?
Yes.
Sir, already I have asked the question, sir. Again, I repeat, sir.
Is it the problem is from my side? Then I will change the connection.
I think sir, some network issue.
Hello.
Some internet problem, sir.
Some network issue is there, sir.
Let me log in from my mobile. My side.
Sir.
No.
I think, sir, your side, sir.
Yes.
Hello, sir.
It is not audible properly.
sir, you are audible, sir. Hello.
Your voice is audible.
Hello.
Yes, sir, you are
Hello.
audible, sir.
Hold on for few seconds, few minutes.
Okay.
I'll join through my mobile.
Okay. No issue.
Yeah. Actually, the questions are not audible to me.
Okay, sir, I will repeat it.
Hello.
Hello, sir.
Okay, hold on for few minutes.
Yes.
Hello.
Sir.
Hello, sir.
Just hold on.
Yes, sir.
Hold on. I'm just joining soon through my mobile.
Mm-hmm.
Yes. I'm not. It is not audible to me.
Hello, sir.
Hello. I think some network issue. So we are waiting. So for the Rakesh sir, try to rejoining.
Yes, sir. Okay, sir. We can conclude the session. If sir is not coming.
Hello.
Hello, sir. Hello, sir.
Yes. Yes, sir. You are audible, sir. Hello.
Hello, sir.
Microphone is muted.
Yes, sir. Microphone is muted, sir.
Am I audible to you? Yes. But your voice is not coming properly to me.
Okay. Now?
Hello, sir.
Yes,
Hello.
yes, sir. You are audible, sir.
So if I am audible, so please write down the question in the chat box such that I can answer.
Okay, participant, have you any queries? Please write down your question in chat box.
Okay, sir. Okay, sir.
If I am audible, then I can answer, na?
Yes, yes.
So that
Yes,
is
sir.
not a problem because I am not able to hear you.
Sir.
Yes.
Sir, I have written in the chat box. Why sound element are taken as phase shifting? Phase shifting.
Actually, you are
element.
not audible to me.
Oh.
Same problem with Kalyan sir also.
Sir, am I audible?
I think from our expert side, there is some network issue.
No.
Hello?
Hello?
You can. Hello. Professor Kalyan, you are not audible to me. I don't know what about others.
Actually, we are all audible, but you are not audible to all. That is the main issue, sir. Okay, sir, no problem.
Hello?
Hello.
Actually, না 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 ঠিক আছে
Okay, I think some network issue from our expert side, Dr. Rakesh Sinha. So, thank you to our respected expert in session 3, Dr. Rakesh Sinha, for giving his valuable lecture and sharing his practical knowledge on two-port network or multi-port network. So thank you very much, and just I am concluded this session 3 for days 1 in faculty development program. So thank you all the participants for joining us and for your patience. And tomorrow we will join